Welcome to The Calm Scientist. If you're here, it probably means you're ready to slow down, relax, and drift gently into the night with a head full of curiosity. Tonight we're going to unravel one of the most peculiar stories in all of natural history, the utterly bizarre and improbable tale of how humans came to be. It's the kind of bedtime story only evolution could write, full of plot twists that no screenwriter would dare attempt, characters that vanished without explanation, and an ending so unlikely that if you pitched it to nature itself, she might laugh and suggest something more believable. I hope this isn't terribly inconvenient for your plans to fall asleep, because as we explore why human evolution is so wonderfully weird, you might find yourself pondering how a species that should have been extinct millions of years ago ended up contemplating the stars from the comfort of their beds. Before we begin, if you're enjoying this gentle stroll through our evolutionary oddities, I'd be deeply grateful if you gave the video a like and subscribed. It really helps this peaceful little channel drift along through the vast ocean of the internet. And if you're feeling particularly friendly tonight, let me know in the comments where in the world you're listening from and what time it is where you are. I cherish imagining our little constellation of sleepy minds scattered across time zones, all connected by the same wonderment about how we ended up as these peculiar, upright apes pondering our own existence. This video is here to relax you, to fascinate you just enough to make your thoughts soft and meandering as we explore the impossible bodies we inhabit, the mystery of why we decided to walk on two legs, and the lost cousins we once shared this planet with. You won't need to remember anything, just float with me as we wander through the twisted pathways of human evolution. And just before we begin, this video is for relaxation and education. It is not medical advice or a substitute for professional care. Always look after yourself and sleep well. Let's start with the basics, or what seem like the basics until you really think about them. Human evolution sounds like a straightforward story. Ape-like ancestors gradually became more human-like over millions of years until, eventually, we emerged as the clever species writing bedtime stories about science on the internet. But hold that thought gently, because, as it turns out, even something as fundamental as human evolution is much more slippery and strange than it appears. We are, by almost any biological measure, completely ridiculous creatures. Think about that for a moment. If you were designing an animal from scratch, you would never, ever create something like a human being. We are a collection of evolutionary compromises, bizarre adaptations, and frankly improbable solutions to problems that other animals solved much more elegantly. We're the biological equivalent of a house that's been renovated so many times by different architects that it no longer makes architectural sense, yet somehow it still stands and even manages to be oddly charming. The impossible body, why humans are biological absurdities. There's something quietly magnificent about your sleeping body right now. Something that would puzzle any alien biologist trying to understand how such a creature could possibly exist. You're lying there, breathing steadily, your heart beating its reliable rhythm, your brain cycling through its nightly maintenance routines, and every cell in your body is participating in the impossible experiment of being human. Let's examine this remarkable vessel you inhabit, this biological puzzle that evolution somehow managed to solve despite all logic suggesting it shouldn't work. Your body is a testament to the fact that evolution doesn't plan ahead, doesn't optimize for elegance, and certainly doesn't worry about making sense to future scientists trying to understand how you came to be. Consider your brain first, that 3-pound universe nestled in your skull. It sounds like such a modest thing when described that way, doesn't it? 3 pounds of tissue, roughly the weight of a small laptop, consuming about 20% of your body's total energy, even when you're doing nothing more strenuous than listening to someone talk about evolution. But here's where things get interesting, and by interesting I mean completely absurd from an engineering perspective. Your brain is preposterously large for an animal of your size. If you were to scale up a typical mammal to human proportions, its brain would be roughly the size of a walnut. Your actual brain is about 7 times larger than what mammalian scaling laws suggest it should be. It's as though nature looked at the perfectly reasonable brain size that physics and metabolism suggested for a creature your size and decided to say, well, let's see what happens if we make it enormous and figure out the consequences later. The consequences, as it turns out, are numerous and fascinating. That oversized brain requires a constant supply of glucose and oxygen, making you remarkably vulnerable to interruptions in either. While other animals can survive significant periods without food or oxygen, your massive neural networks begin shutting down within minutes of being deprived of either resource. You are, in essence, a creature whose survival depends entirely on keeping a metabolically expensive organ happy, an organ that could have been much smaller and still allowed you to function perfectly well as a medium-sized primate. But wait, there's more. That enormous brain had to fit somewhere, which meant your skull had to expand to accommodate it. This created a cascade of problems that evolution had to solve on the fly, so to speak. A larger skull meant a larger head, which meant your birth canal had to be wider, which meant your pelvis had to be restructured, which meant the way you walk had to change, which meant your entire spine had to be redesigned. One change demanded another and another, until your entire body plan was reorganized around the demands of housing an inexplicably large brain. Meanwhile, your skull was facing additional challenges. To make room for all that neural tissue, something had to give, and what gave were your jaw muscles. Your ancestors had massive, powerful jaws capable of cracking nuts and processing tough plant material. You have what can only be described as adorably tiny jaw muscles, so weak that you can barely manage to chew through a piece of reasonably tough meat without tools to help you. This trade-off between brain space and jaw strength would have been fatal for most species. After all, if you can't process food efficiently, you die. But humans stumbled upon an external solution. We invented cooking. By applying heat to food, we essentially began pre-digesting our meals outside our bodies, making it possible to extract nutrients without needing the massive jaw muscles that other primates possess. It's a bit like realizing your car engine is too small for the hills in your area, so instead of getting a bigger engine, you decide to move all the hills. Let's take a closer look at your peculiar hair situation, because even your hair growth patterns tell the story of a species that evolution couldn't quite figure out what to do with. You are, technically speaking, a naked ape, but not entirely naked. You've retained hair in very specific locations, while losing it almost everywhere else, creating a pattern that serves no obvious purpose and has puzzled scientists for decades. Most mammals are covered in hair because hair provides insulation, protection from the sun, and protection from parasites. You have essentially abandoned this system, leaving your skin exposed to the elements, yet you've retained dense hair growth on your head, in your armpits, and around your reproductive organs. It's as though evolution was in the middle of removing your hair and got distracted partway through the process. The leading theories for why humans lost most of their body hair range from plausible to wonderfully speculative. Perhaps our ancestors spent significant time in water, where hair would have been a hindrance. Perhaps we needed to cool more efficiently as we became persistence hunters, chasing prey across vast distances under the African sun. Perhaps the loss of hair helped us avoid parasites as we began living in larger social groups. Or perhaps, as some scientists suggest, it was simply a side effect of sexual selection, with early humans preferring mates with less body hair for reasons we can only guess at. What's remarkable is that losing your hair should have been an evolutionary disaster. Hair protects skin from ultraviolet radiation, helps regulate body temperature, and provides a first line of defense against cuts and abrasions. By becoming essentially hairless, humans became dramatically more vulnerable to skin cancer, hypothermia, and injury. The fact that we survived this transition suggests that whatever advantages hairlessness provided must have been extraordinary, though we're still not entirely certain what those advantages were. Your skin itself tells another part of the story of human evolutionary peculiarity. Unlike most mammals, human skin can tan, developing additional pigmentation in response to sun exposure. This is a sophisticated biological mechanism that allows you to adjust your protection against ultraviolet radiation based on environmental conditions. It's the kind of adaptation you'd expect to see in a species that moved between dramatically different climates, which is exactly what early humans did as they spread across the globe. But even your skin's ability to tan reveals the constraints evolution was working under. Darker skin provides better protection against UV radiation, but makes it harder to synthesize vitamin D in low-light conditions. Lighter skin allows for better vitamin D synthesis, but provides less protection against sun damage. Human populations developed different baseline skin pigmentations as they adapted to different latitudes, creating a situation where your skin color reflects the angle of the sun your ancestors lived under for thousands of years. There's something deeply poetic about the fact that you can determine roughly where someone's ancestors lived just by looking at their skin, as though each human carries a map of their family's long journey across the planet written in melanin and encoded in their DNA. Speaking of your DNA, let's consider the genetic peculiarities that make humans so unusual among primates. You share roughly 98.8% of your DNA with chimpanzees, your closest living relatives. That sounds like a lot, and it is. But that remaining 1.2% contains some of the most dramatic genetic innovations in evolutionary history. For perspective, consider that you share about 90% of your DNA with cats, roughly 85% with mice, and approximately 60% with fruit flies. The genetic difference between you and a chimpanzee is actually quite small in the grand scheme of biological diversity, yet it encompasses the difference between a species that makes simple tools and a species that builds rockets to visit other planets. Most of the genetic differences between humans and chimpanzees don't involve completely new genes, but rather changes in how existing genes are regulated, when they're activated, and how intensely they're expressed. It's a bit like the difference between two orchestras playing the same basic instruments but with completely different conductors interpreting the music. The instruments are nearly identical, but the resulting symphonies are entirely different. One of the most significant changes involves genes that control brain development. In humans, these genes remain active much longer during development, allowing the brain to continue growing and adding neural connections well into childhood and adolescence. A chimpanzee brain reaches adult size relatively quickly, while human brains continue developing for decades. This extended period of brain growth requires an extended period of childhood dependency, creating the uniquely human phenomenon of adolescence. This brings us to another evolutionary peculiarity. Humans have the longest childhood of any mammal relative to their adult lifespan. A mouse reaches sexual maturity in weeks, a chimpanzee in years, but humans require nearly 2 decades to fully mature. From an evolutionary perspective, this is enormously risky. The longer you remain dependent on your parents, the more opportunities there are for something to go wrong before you can reproduce and pass on your genes. Most species solve the problem of brain development by being born with brains that are essentially fully formed and ready to function. Human babies are born with brains that are barely functional, requiring years of learning and development before they can survive independently. You are essentially born premature compared to other mammals, with a brain so underdeveloped that you couldn't even lift your own head for months. This extended childhood is possible only because humans developed sophisticated social structures to support it. Human children require not just parents but entire communities to reach maturity successfully. No other species invests so much collective energy in raising their young, and no other species requires such an investment for their young to survive. But here's where things get interesting in that uniquely human way. That extended period of brain development and learning, combined with sophisticated social structures, created the possibility for culture. Human children don't just learn basic survival skills during their long childhood, they absorb entire systems of knowledge, language, customs, and technologies that have been accumulated over generations. This cultural inheritance is as important to human survival as genetic inheritance, perhaps more so. A human baby raised without exposure to human culture will never develop normal language, social skills, or technological abilities, regardless of their genetic potential. Culture, in other words, has become part of human biology, a form of inheritance that exists outside the genome but is essential for the genome to express itself successfully. Let's delve deeper into the mystery of human metabolism, because even the way your body processes energy reveals how strange our evolutionary path has been. Human beings have remarkably high metabolic rates for mammals our size, burning through calories at a pace that should, by all rights, make us unsustainable as a species. Your brain alone, as we mentioned, consumes about 20% of your daily energy budget. Your muscles, even at rest, consume another 25%. Your heart, liver, and kidneys together account for another 30%. By the time you add up all the energy requirements of simply being human, you're left with very little metabolic budget for actually doing anything. Compare this to other primates, who spend the majority of their day foraging for food and can survive quite well on relatively low-quality vegetation. Chimpanzees can meet most of their nutritional needs by eating leaves, bark, and occasional insects. You, on the other hand, require a constant supply of high-quality nutrients to keep your oversized brain and metabolically expensive body functioning. This created what biologists call the expensive tissue hypothesis. To support the energy demands of a large brain, something else had to shrink. In humans, what shrank was the digestive system. Your gut is remarkably small compared to other primates, with a correspondingly reduced ability to extract nutrients from low-quality food sources. This trade-off between brain size and gut size essentially forced early humans into a high-risk, high-reward evolutionary strategy. We became obligate consumers of high-quality food, which meant we had to become extremely good at finding, processing, and sharing nutritious resources. This drove the development of increasingly sophisticated tools, hunting strategies, and social cooperation. But it also made us remarkably fragile. While a chimpanzee can survive for weeks on whatever vegetation it can find, humans begin experiencing serious health problems within days of inadequate nutrition. We became a species entirely dependent on our ability to outsmart our environment, because we could no longer survive by simply eating whatever was available. This metabolic vulnerability helps explain why humans developed such elaborate food processing technologies so early in our evolutionary history. Cooking, as mentioned earlier, essentially allows us to pre-digest food using external heat sources. But humans also developed fermentation, drying, smoking, and numerous other techniques for making nutrients more accessible and preserving food for periods of scarcity. We became, in essence, a species that survives by manipulating our environment rather than adapting to it. While other animals evolved larger digestive systems to process tough plant material, humans evolved bigger brains to figure out how to make plant material easier to digest. While other animals evolved thicker fur to survive cold climates, humans evolved the intelligence to make clothing and shelter. This pattern of using intelligence to solve problems that other species solve through biological adaptation became the defining characteristic of human evolution. We are the species that stopped evolving physically and started evolving culturally, using our brains to build the tools and systems that other species developed through natural selection. Let's examine the peculiarities of human reproduction, because even the way we make more humans is bizarre compared to other mammals. Human reproduction is, from a biological perspective, remarkably inefficient and unnecessarily complicated. Consider human pregnancy. At 9 months, human gestation is actually relatively short for a mammal our size, but it produces offspring that are essentially helpless for years afterward. Most mammals give birth to young that can walk within hours or days. Human babies can't even support their own heads for months and don't reach basic mobility for nearly a year. This is partly due to the constraints imposed by that oversized brain we discussed earlier. Human babies are born with brains that are only about 25% of their adult size, whereas most mammals are born with brains that are already 60 to 70% of adult size. Human brains have to do most of their growing outside the womb, which means human babies are born in a remarkably underdeveloped state. But even more peculiar is the way human females have concealed ovulation. Most mammalian females advertise their fertility quite obviously, developing visible signs that inform males when reproduction is possible. Human females show virtually no external signs of ovulation, making it difficult even for the female herself to know exactly when she's fertile without careful attention to subtle physiological changes. This concealed ovulation has puzzled evolutionary biologists for decades. Why would natural selection favor a system that makes reproduction less efficient? The leading theories suggest that concealed ovulation encouraged pair bonding between males and females, since males couldn't simply wait for obvious signs of fertility before investing time and energy in potential mates. Human pair bonding itself is unusual among mammals. Most mammalian species are either solitary or live in social groups where reproduction is dominated by a few high-status males. Humans developed a system of long-term pair bonds between males and females, with both parents investing heavily in raising offspring together. This system of pair bonding and cooperative child-rearing was probably essential for raising human children, given their extended period of dependency. A single parent simply couldn't provide the resources and protection necessary for a human child to reach maturity. But it also created the foundation for the complex social structures that characterize human societies. Human social behavior reveals another layer of evolutionary peculiarity. We are simultaneously one of the most cooperative and most competitive species on Earth. Humans regularly sacrifice their own interests for the benefit of complete strangers, displaying levels of altruism that exceed even those found in social insects like ants and bees. Yet humans are also capable of extraordinary violence and cruelty, often directed at members of their own species. No other animal exhibits quite this combination of extreme cooperation within groups and extreme hostility between groups. We are the species that will rush into burning buildings to save strangers and simultaneously wage wars that kill millions. This contradiction reflects the evolutionary pressures that shaped human social behavior. Early humans lived in small, tightly knit groups where cooperation was essential for survival. Everyone in the group was either a relative or a potential mate, so helping group members was essentially helping yourself by proxy. But different groups were often in competition for the same resources, creating strong pressure for group loyalty and suspicion of outsiders. Modern humans inherited these ancient psychological tendencies, creating the paradox of a species that is capable of remarkable empathy and cooperation within their perceived in-group while being capable of dehumanizing and destroying perceived out-groups. Understanding this aspect of human nature is crucial for understanding both our greatest achievements and our most terrible failures as a species. Let's take a closer look at human communication, because the way we share information with each other represents another dramatic departure from typical mammalian behavior. Human language is unlike any other animal communication system in its complexity, flexibility, and capacity for abstract thought. Most animal communication involves relatively simple signals that convey immediate, practical information. A bird's alarm call warns of predators. A bee's dance communicates the location of flowers. A wolf's howl coordinates pack activities. These are all sophisticated forms of communication, but they're fundamentally different from human language in their scope and flexibility. Human language can communicate not just about immediate concrete realities, but about abstract concepts, hypothetical situations, and events that occurred in the past or might occur in the future. You can use language to describe mathematical concepts that have no physical existence, to tell stories about imaginary characters, or to share knowledge about events that happened before you were born. This capacity for abstract communication allowed humans to accumulate knowledge across generations in ways that no other species can match. Each generation could build upon the discoveries and innovations of previous generations, creating an exponential increase in the complexity of human culture and technology. But human language also reveals some interesting constraints on human cognition. Despite our linguistic sophistication, humans are remarkably bad at thinking about certain types of problems, particularly those involving large numbers, long timescales, or complex systems with multiple interacting variables. This suggests that human intelligence evolved to solve specific types of problems faced by our ancestors, living in small social groups, hunting animals, gathering plants, and navigating complex social relationships. We're extremely good at understanding the intentions and emotions of other humans, predicting the behavior of animals and manipulating physical objects to achieve goals. We're much less good at understanding statistical relationships, thinking about exponential growth, or predicting the long-term consequences of complex systems. These limitations help explain why humans consistently struggle with problems like climate change, economic planning, and public health measures that require thinking about large-scale, long-term consequences. The mystery of bipedalism, why we stand alone. Now, let's turn our attention to perhaps the most distinctive feature of human anatomy, the fact that you're designed to walk upright on 2 legs rather than 4. This might seem like a simple change, but bipedalism represents one of the most dramatic and mysterious transitions in all of evolutionary history. Walking upright sounds like an obviously superior way to get around, doesn't it? It frees up your hands for tool use, gives you a better view of the surrounding landscape, and creates the upright, dignified posture that we associate with human intelligence and nobility. But here's the thing that makes bipedalism so puzzling. It's actually a terrible way for a medium-sized mammal to move around. Quadrupedal locomotion, walking on 4 legs, is faster, more stable, more energy efficient, and less prone to injury than bipedal locomotion. A chimpanzee moving through the forest can easily outrun a human on foot. A quadrupedal animal can change direction more quickly, maintain balance more easily, and recover from stumbles more effectively than a bipedal one. Yet somewhere around 6 or 7 million years ago, the ancestors of humans began the long, strange process of transitioning from efficient quadrupedal apes to inefficient bipedal apes. This transition required a complete reorganization of the skeleton, musculature, and nervous system, and it took millions of years to complete. Think about the engineering challenges involved in converting a quadrupedal ape into a bipedal one. The spine had to develop an S-shaped curve to balance the body over the legs. The pelvis had to be completely restructured to support the weight of the upper body. The legs had to be lengthened and strengthened. The feet had to be redesigned from grasping appendages into stable platforms for walking. Meanwhile, the skull had to be repositioned so that the head balanced properly on top of the spine, rather than projecting forward as it does in quadrupedal animals. This required changes to the neck muscles, the jaw structure, and the way the skull attaches to the spine. Each of these changes created problems that required additional changes. The narrower pelvis needed for efficient bipedal locomotion made childbirth more difficult and dangerous. The longer legs made it harder to climb trees. The restructured feet lost much of their grasping ability. The S-shaped spine became prone to problems like lower back pain that virtually never affect quadrupedal animals. From an engineering perspective, bipedalism looks like a solution in search of a problem. It's as though our ancestors decided to rebuild a perfectly functional four-wheel drive vehicle into a unicycle, making it more difficult to operate, less stable, and more prone to catastrophic failure, but somehow more interesting to ride. So why did early humans make this transition? The honest answer is that we're not entirely certain, and the various theories proposed by scientists reveal just how puzzling this evolutionary change really is. One possibility is that bipedalism evolved as an adaptation to a changing environment. Around the time that early humans began walking upright, the climate in Africa was becoming cooler and drier, and forests were giving way to more open woodlands and grasslands. Perhaps walking upright provided advantages in this new environment, allowing early humans to see over tall grass, travel more efficiently between scattered trees, or keep cooler by exposing less body surface to the sun. The thermoregulation hypothesis suggests that standing upright helped early humans stay cool by reducing the amount of body surface exposed to direct sunlight during the hottest part of the day. When the sun is directly overhead, a quadrupedal animal has its entire back exposed to solar radiation, while a bipedal animal exposes only the top of its head and shoulders. This might seem like a minor advantage, but temperature regulation is crucial for animals with large brains. Brain tissue is extremely sensitive to overheating, and even small increases in body temperature can impair cognitive function. If early humans were already developing larger brains, staying cool might have been essential for survival. Another possibility is that bipedalism evolved as an adaptation for long-distance travel. Early humans may have needed to walk long distances to find food, water, or mates as their environment became more fragmented. While bipedal locomotion is slower than quadrupedal locomotion over short distances, it might be more energy efficient over very long distances. Modern humans are actually remarkably good long-distance travelers on foot. A healthy human can walk 20 to 30 miles per day for weeks on end, covering distances that would challenge most other mammals. This endurance capability might have been crucial for early humans living in patchy environments where resources were scattered across large areas. The aquatic ape hypothesis, while controversial, suggests that early humans spent significant amounts of time in and around water, which would have favoured upright locomotion. Walking upright is much more efficient than quadrupedal locomotion when moving through water, and many of the anatomical changes associated with human evolution, such as the loss of body hair and the development of subcutaneous fat, are consistent with a semi-aquatic lifestyle. While most scientists are skeptical of the fully aquatic version of this hypothesis, it's possible that early humans spent enough time foraging in shallow water, crossing rivers, or living near coastlines to make bipedal adaptations advantageous. The provisioning hypothesis suggests that bipedalism evolved to facilitate food sharing and childcare. standing upright frees the hands for carrying food, tools, and infants, which would have been essential for the cooperative child-rearing that characterizes human societies. Early human females carrying helpless infants would have needed to transport food and tools while keeping their hands free for childcare. This hypothesis is attractive because it connects bipedalism to other uniquely human characteristics like extended childhood, pair bonding, and cooperative social behavior. It suggests that the physical changes associated with walking upright were part of a larger package of adaptations related to social cooperation and childcare. The sexual selection hypothesis proposes that bipedalism evolved because early humans found upright posture attractive in potential mates. This might seem frivolous, but sexual selection has driven some remarkable evolutionary changes in other species. Perhaps early humans preferred mates who could walk upright more effectively, gradually selecting for the anatomical changes that made bipedalism possible. This hypothesis gains some support from the observation that human sexual behavior is quite different from that of other primates. Humans are one of the few primate species where males and females are roughly similar in size, suggesting that physical competition between males may have been less important than other factors in determining mating success. Whatever the original advantage of bipedalism, once early humans committed to this form of locomotion, it set in motion a cascade of changes that would reshape virtually every aspect of human anatomy and behavior. Walking upright changed the way humans interacted with their environment, the foods they could access, the tools they could use, and the social structures they could maintain. The transition to bipedalism also reveals something important about the nature of evolution itself. Evolution doesn't optimize for perfection. It only requires that changes be good enough to improve survival and reproduction slightly. The fact that bipedalism involves numerous trade-offs and compromises doesn't matter, as long as the net effect is positive. Humans today live with the consequences of those ancient trade-offs. Lower back pain, knee problems, and complications during childbirth are all prices we pay for our ancestors' decision to walk upright. Yet the same anatomical changes that create these problems also made possible the manual dexterity, tool use, and cognitive development that define human civilization. Let's examine more closely how bipedalism changed human anatomy, starting with the pelvis. The human pelvis is a masterpiece of evolutionary compromise, simultaneously adapted for efficient locomotion, childbirth, and organ support. No other animal has quite the same challenges in pelvic design, because no other animal needs to balance all these requirements. In quadrupedal animals, the pelvis is relatively simple. It needs to support the weight of the abdominal organs, provide attachment points for the leg muscles, and create a birth canal for offspring. The birth canal can be relatively large because there's plenty of space, and the orientation of the pelvis doesn't constrain the size or shape of the pelvic opening. The human pelvis had to be completely redesigned for bipedal locomotion. To walk efficiently on two legs, the pelvis needs to be narrower and more upright than in quadrupedal animals. This creates better leverage for the muscles that move the legs and helps maintain balance during walking. But a narrower pelvis creates a smaller birth canal, which becomes problematic when combined with the larger skull size needed to accommodate human brains. Human birth is dramatically more difficult and dangerous than birth in other primates, specifically because of this conflict between the demands of bipedal locomotion and the needs of large-brained offspring. This constraint helps explain why human babies are born in such an underdeveloped state compared to other mammals. Human babies must be born before their skulls become too large to fit through the birth canal, which means they're born with much more growing and developing to do outside the womb. The human spine tells another part of the bipedalism story. Quadrupedal animals have relatively straight spines that function essentially as bridges, with the weight of the body suspended below. This is a mechanically efficient design that distributes weight evenly and creates minimal stress on individual vertebrae. The human spine had to develop a complex S-shaped curve to balance the body over the legs while maintaining an upright posture. This curve allows humans to walk efficiently while keeping the head positioned properly for forward vision, but it also creates stress points where back problems commonly develop. The lower back, in particular, bears enormous stress in bipedal humans. The lumbar spine must support the entire weight of the upper body while allowing for the flexibility needed for walking, bending, and twisting. This is a mechanically challenging task that quadrupedal spines never face. Human feet represent another fascinating example of evolutionary engineering. The feet of other primates are essentially hands, with long flexible toes and a thumb-like big toe that can grasp branches and objects. These feet are excellent for climbing and grasping, but relatively poor for efficient walking on the ground. Human feet were redesigned as platforms for bipedal locomotion. The toes became shorter and lost most of their flexibility. The big toe was brought into alignment with the other toes and lost its opposability. The arch of the foot was developed to provide spring and shock absorption during walking. These changes made human feet excellent for walking and running on the ground, but terrible for climbing. While other primates can move through trees with ease using their grasping feet, humans are clumsy climbers who must rely primarily on arm strength to ascend vertical surfaces. The human foot also developed a unique mechanism for storing and releasing energy during walking. The arch of the foot compresses slightly when weight is applied, and then springs back, providing a small boost of energy with each step. This mechanism, combined with the elastic properties of various tendons and ligaments in the leg, makes human walking remarkably energy efficient once momentum is established. Interestingly, this energy storage and release system works best at moderate walking speeds. Humans are less efficient at very slow speeds, where the energy storage mechanism doesn't have time to work properly, and at very fast speeds, where the system becomes overwhelmed. This suggests that human locomotion evolved for sustained moderate speed travel, rather than quick sprints or slow foraging. The changes in human limb proportions also reflect adaptations for bipedal locomotion. Humans have relatively long legs compared to their arms, unlike other apes which have long arms and relatively short legs. This change in limb proportions improves the efficiency of bipedal walking by increasing stride length and improving the mechanical advantage of the leg muscles. But longer legs also mean a higher centre of gravity, which makes balance more challenging. Humans compensate for this with sophisticated neural control systems that constantly make tiny adjustments to maintain stability during walking. These balance systems are so complex and finely tuned that engineers are still struggling to replicate them in bipedal robots. The transition to bipedalism also required changes in the muscles and nervous system. Walking upright requires a completely different pattern of muscle activation than quadrupedal locomotion. The gluteal muscles, which are relatively small in other apes, became much larger in humans to provide the power needed for efficient bipedal walking. The nervous system had to develop new motor programs for coordinating bipedal locomotion. The pattern of neural activity that controls human walking is fundamentally different from that used by quadrupedal animals. This neural reorganization probably took many generations to perfect, during which early bipedal humans were likely quite clumsy compared to their quadrupedal relatives. Modern humans take bipedal locomotion for granted, but learning to walk upright is actually an extraordinary developmental achievement. Human infants spend months learning to coordinate the complex muscle movements and balance adjustments required for stable bipedal locomotion. Even then, young children fall frequently as they master this mechanically challenging form of movement. The fact that humans invested so much evolutionary time and effort in developing bipedal locomotion, despite its many disadvantages, suggests that the benefits must have been substantial. The freed hands made possible the development of increasingly sophisticated tools. The upright posture improved long-distance vision and may have facilitated better temperature regulation. The changes in pelvic structure and reproductive anatomy set the stage for the evolution of larger brains and more complex social behaviors. But perhaps most importantly, bipedalism made humans distinctly human. No other primate has committed fully to upright locomotion, and this single change created a cascade of anatomical and behavioral modifications that would eventually lead to language, culture, technology, and all the other characteristics that distinguish humans from other animals. In a sense, the decision to walk upright was the first step, literally and figuratively, on the long journey from tree-dwelling ape to spacefaring human. It was a gamble that paid off spectacularly, though it took millions of years for the full benefits to become apparent. Lost cousins, the vanished hominins who shared our world. As you drift deeper into relaxation tonight, let's wander into one of the most haunting chapters of human evolution, the story of our lost cousins, the other human species who once walked this earth alongside our ancestors, but ultimately vanished into the mists of prehistory. It's the kind of story that makes you wonder about roads not taken, about what the world might have looked like if evolution had unfolded differently, and about the thin threads of chance that led to your existence tonight, listening to these words in the comfort of your bed. For most of human history, we believed we were alone, the single human species that had emerged from our ape-like ancestors to inherit the Earth. This narrative was both comforting and lonely, suggesting that we were evolution's chosen species, unique and destined for intelligence, but also that we'd always been solitary in our humanity. The truth, as it so often does, turned out to be much stranger and more wonderful than our simple stories suggested. Humans were not alone for most of our evolutionary history. We shared this planet with multiple other human species, our close relatives who were recognizably human but distinctly different from us in their anatomy and their cultures, and perhaps their ways of understanding the world. These weren't primitive proto-humans or evolutionary stepping stones on the path to modern humanity. They were fully realized human species with their own evolutionary trajectories, their own adaptations, their own technologies, and their own ways of being human. Some of them lived alongside our direct ancestors for hundreds of thousands of years. Some of them contributed genes that you still carry in your cells tonight. Some of them created art, buried their dead, and gazed at the same stars you might glimpse through your window. The most famous of these lost cousins are the Neanderthals, whose name has become synonymous with primitive brutishness in popular culture, but whose reality was far more sophisticated and poignant than our stereotypes suggest. Neanderthals weren't our ancestors, they were our relatives, a separate lineage of humans who split from our family tree roughly 400,000 to 600,000 years ago, and then evolved independently in the challenging environments of Ice Age Europe and Western Asia. Imagine, if you will, a parallel human civilization developing over hundreds of thousands of years, adapting to frozen landscapes and massive glaciers, developing their own tools and cultures and ways of understanding existence, all while our own ancestors were pursuing their own evolutionary path in Africa. It's a bit like imagining an alternate history where two different human societies developed on separate continents, never knowing of each other's existence until they finally met after millennia of independent development. Neanderthals were magnificently adapted to their harsh environments. They were shorter and more robust than modern humans, with powerful muscles, thick bones, and bodies built for retaining heat in frigid climates. Their skulls were elongated and low, with prominent brow ridges and large nasal cavities that helped to warm the cold air they breathed. Their brains were actually larger than those of modern humans on average, though shaped differently, with less development in areas associated with language and abstract thinking, but more development in areas related to visual processing and motor control. These weren't the shambling, grunting cave dwellers of popular imagination. Neanderthals were skilled toolmakers who developed sophisticated techniques for crafting spear points, scrapers, and cutting implements. They controlled fire, built shelters, and survived in environments that would challenge even modern humans with all our technology. They hunted massive animals like mammoths and woolly rhinoceros, requiring extraordinary coordination, planning, and courage. Recent archaeological discoveries have revealed that Neanderthals had rich cultural lives that we're only beginning to understand. They created cave paintings, fashioned jewelry from shells and animal teeth, and buried their dead with what appears to be ritualistic care. Some Neanderthal burial sites contain evidence of flowers and other grave goods, suggesting they had concepts of death, loss, and perhaps even an afterlife. They may have had language, though probably not as complex as modern human language. Their hyoid bones, which support the structures needed for speech, were similar to those of modern humans. Their DNA contains versions of genes associated with language development in modern humans. They almost certainly communicated in sophisticated ways, sharing knowledge about tool-making, hunting strategies, and survival techniques that allowed them to thrive in challenging environments for hundreds of thousands of years. But perhaps the most remarkable discovery about Neanderthals is that they didn't simply vanish without a trace. When modern humans migrated out of Africa and into Europe and Asia roughly 45,000 to 60,000 years ago, they encountered Neanderthal populations that had been living in those regions for hundreds of thousands of years. What happened next was one of the most significant meetings in the history of life on Earth. These two human species, separated by hundreds of thousands of years of independent evolution, met, interacted, and in some cases, fell in love and had children together. We know this because modern humans of European and Asian descent carry Neanderthal DNA in their genomes. If you have European or Asian ancestry, roughly 1 to 4% of your DNA came from Neanderthal ancestors who lived tens of thousands of years ago. Every time your immune system fights off an infection, every time your body processes certain foods, every time particular genes influence your appearance or metabolism, you may be benefiting from genetic innovations that evolved in Neanderthal populations adapting to Ice Age environments. This genetic legacy means that Neanderthals didn't truly go extinct. Part of them lives on in billions of modern humans, a ghostly presence in our genomes that connects us to those ancient people who survived in frozen landscapes, created beautiful cave art and loved their children enough to bury them with flowers. But why did Neanderthals as a distinct species disappear while modern humans continue to thrive and spread? This question has puzzled scientists for decades, and the answer probably involves a combination of climate change, competition for resources, and small but significant differences in social organization and technology. The period when modern humans and Neanderthals coexisted was marked by dramatic climate fluctuations as the last ice age waxed and waned. These environmental changes would have stressed both populations, but modern humans may have had slight advantages in their ability to adapt to changing conditions. Modern humans appear to have lived in larger, more complex social groups, which may have given them advantages in sharing information, coordinating hunts, and supporting members during difficult times. Modern humans also developed more sophisticated long-distance projectile weapons such as spear throwers and eventually bows and arrows, which may have given them hunting advantages over Neanderthals, who relied primarily on thrusting spears and close-contact hunting. Small technological differences like these could have been crucial when both populations were competing for the same prey animals and territory. Population size may have been the crucial factor. Neanderthal populations appear to have been relatively small and scattered, while modern human populations were larger and more densely connected. In evolutionary terms, larger populations have significant advantages. They're more resistant to environmental catastrophes, they generate innovations more quickly, and they're less likely to suffer from the genetic problems that can affect small, isolated groups. As climate change and competition stressed both populations, the larger, more connected modern human groups may have been able to weather the challenges while smaller Neanderthal groups gradually disappeared. It wasn't necessarily a dramatic conquest or replacement. It may have been more like a slow fading as Neanderthal populations became smaller and more isolated until they could no longer maintain viable breeding groups. The last known Neanderthal populations disappeared from their final refuges in southern Spain roughly 28,000 years ago. By that time, modern humans had spread across Europe, Asia, and were beginning to colonize Australia and the Americas. The world had become a much lonelier place for human intelligence, though few would have realized it at the time. But Neanderthals weren't the only other human species our ancestors encountered. In 2008, scientists analyzing DNA from a tiny finger bone found in a cave in Siberia discovered evidence of yet another human lineage, one so unknown that it could only be identified through its genetic signature. These mysterious relatives have been named Denisovans after the cave where they were first discovered. Denisovans are perhaps even more enigmatic than Neanderthals because we have so little physical evidence of their existence. The entire knowledge of Denisovan anatomy comes from a handful of bone fragments and teeth found in a single cave in the Altai Mountains of Siberia. Yet their genetic legacy tells us they were a distinct human lineage that split from the ancestors of both modern humans and Neanderthals roughly 400,000 to 500,000 years ago. What makes Denisovans particularly fascinating is the geographic scope of their genetic influence. While Neanderthal DNA is found primarily in people of European and Asian descent, Denisovan DNA appears in populations from New Guinea, Australia, and parts of Southeast Asia. This suggests that Denisovans had a much wider geographic range than the small area where their physical remains have been found. The fact that Denisovan genes appear in Australian and New Guinean populations is particularly intriguing because it means these ancient humans must have been present in Southeast Asia when modern humans were migrating toward Australia roughly 50,000 years ago. Modern humans not only encountered Denisovans during this migration, but interacted with them closely enough to produce hybrid offspring whose genes survived in their descendants. Some of the Denisovan genes found in modern populations appear to provide advantages for living at high altitudes or in other challenging environments. Tibetan populations carry Denisovan genes that help them process oxygen more efficiently in the thin air of the Himalayan plateau. It's as though these ancient encounters with other human species provided modern humans with genetic tools for surviving in environments our African ancestors had never experienced. The cave where Denisovan remains were found has yielded even more surprises. DNA analysis of the sediments in the cave has revealed genetic material from Neanderthals as well as Denisovans, suggesting that this single location was used by multiple human species over thousands of years. In 2018, scientists announced the discovery of a bone fragment from an individual who had one Neanderthal parent and one Denisovan parent, direct evidence that these different human lineages not only coexisted but interbred. This revelation transformed our understanding of human evolution, from a simple linear progression to a complex web of interactions, separations, and reunions. The story of human evolution isn't a single branching tree, but more like a braided river, with multiple channels that sometimes diverge and sometimes come back together, sharing their waters before separating again. Recent genetic studies have suggested that there may have been even more human lineages that we haven't discovered yet. Analysis of modern human genomes reveals traces of DNA that doesn't match any known human species, suggesting encounters with other human populations that have left no fossil record but contributed genes that survive in living people. Scientists have begun referring to these genetic ghosts as archaic human populations, human lineages that diverged from our ancestors hundreds of thousands of years ago, evolved independently for long periods, and then contributed genes to modern human populations through interbreeding. These genetic shadows hint at a human evolutionary landscape that was far more complex and crowded than we previously imagined. In Africa, where modern humans evolved, there's evidence of genetic contributions from at least two different archaic human populations that modern humans encountered as they spread across the continent. These African archaic populations may have been as genetically distinct from modern humans as Neanderthals or Denisovans, but because they lived in tropical environments where bone preservation is poor, we may never find their fossil remains. The picture emerging from genetic studies is of a world where human diversity was far greater than it is today. Instead of a single human species spreading across the globe, there were multiple human lineages, each adapted to different environments and challenges, each with their own cultures and technologies, each representing a different experiment in what it means to be human. Some of these lineages, like the Neanderthals, were beginning to understand in detail. Others, like the Denisovans, remain mysterious despite their genetic legacy. Still others exist only as patterns in DNA, genetic echoes of human populations whose names we'll never know and whose stories we can only guess at. This diversity raises profound questions about what might have been. What technologies might Neanderthals have developed if they had survived another 10,000 years? What art might they have created? What philosophical insights might have emerged from minds that perceive the world differently than ours do? What about the Denisovans, who survived in Asia long enough to contribute genes to the ancestors of modern Australians and New Guineans? What did they know about surviving in diverse environments that modern humans learned from them? What aspects of their culture and knowledge disappeared forever when their lineages ended? And what about the genetic ghost populations in Africa and elsewhere? Human lineages that may have had hundreds of thousands of years to develop their own unique approaches to intelligence, social organization, and understanding the world. What insights into consciousness, creativity, and human potential disappeared with them? The realization that we once shared this planet with other human species also raises questions about our own future. If climate change and resource competition could drive multiple human lineages to extinction in the past, what does that suggest about the fragility of our own civilization? Are we as vulnerable to environmental changes as our relatives were? Or have our technologies and global connectivity given us new forms of resilience? The fact that we carry genes from some of these extinct human lineages also suggests that human evolution didn't end when modern humans became the only surviving human species. We are in a sense hybrid descendants of multiple human lineages, carrying within our genomes the evolutionary innovations and adaptations of several different experiments in human existence. Modern humans are sometimes described as the winners of human evolution, the lineage that survived while others perished. But perhaps it's more accurate to say that modern humans are the inheritors of human evolution, carrying forward not just our own lineage, but genetic contributions from multiple human species that met, mingled, and shared their evolutionary discoveries before some of them faded into extinction. The genes you carry tonight include innovations that evolved in African populations adapting to tropical environments, Neanderthal adaptations to Ice Age Europe, Denisovan adaptations to high-altitude Asian environments, and genetic contributions from archaic populations we're still discovering. You are, in a very real sense, a living repository of human evolutionary experimentation, a walking museum of different approaches to being human. This genetic heritage connects you not just to your recent human ancestors, but to the entire community of human species that once existed. Every time your immune system fights off a pathogen using a Neanderthal gene, every time you process food using a metabolic pathway inherited from an archaic African population, every time you adapt to a challenging environment using genetic tools contributed by Denisovans, you're benefiting from the evolutionary experiments of human lineages that diverged from your direct ancestors hundreds of thousands of years ago. There's something both humble and magnificent about this realization. Humans are not the triumphant victors of evolutionary competition, but the collaborative inheritors of multiple human experiments in consciousness, intelligence, and adaptation. We succeeded not by defeating our relatives, but by incorporating their innovations into our own genetic toolkit. The story of our lost cousins also reminds us that extinction is a constant presence in evolutionary history. The fact that we exist tonight doesn't reflect our inherent superiority or our evolutionary destiny, but rather the contingent outcomes of countless environmental changes, population dynamics, and chance encounters that could have unfolded differently. If the climate had changed differently, if populations had been distributed differently, if technological innovations had emerged in different lineages, we might be living in a world where Neanderthals developed spaceflight, while modern humans remained a small population in Africa, or a world where multiple human species survived to the present day, creating a diversity of human cultures and perspectives that we can barely imagine. The loss of these other human lineages represents one of the great extinctions in the history of consciousness. Each extinct human species took with them unique ways of perceiving, understanding, and interacting with the world. Their forms of intelligence, their cultural innovations, their artistic expressions, their spiritual insights, all disappeared when their lineages ended. Yet in another sense, they survive in the genes and cultural knowledge that modern humans inherited from them. The tools we use, the art we create, the ways we understand ourselves and our world, all build upon foundations that include contributions from multiple human lineages. We are not just the descendants of modern humans, but the inheritors of the entire human evolutionary experiment, the bottleneck when humanity nearly vanished. Let's drift now into one of the most sobering chapters in human evolutionary history, the story of how close our species came to never existing at all. It's the kind of tale that makes you appreciate the improbable chain of survival and reproduction that led to your existence tonight, lying comfortably in your bed, contemplating the vast sweep of time that brought you into being. Roughly 70,000 years ago, something happened that nearly ended the human story before it had properly begun. The evidence for this near-extinction event is written in our DNA, in the remarkable lack of genetic diversity that characterizes our species compared to other animals, and in geological records that tell of environmental catastrophes that would have challenged the survival of any species. Modern humans are, genetically speaking, an unusually uniform species. If you were to compare the genetic diversity within human populations to the genetic diversity within populations of other mammals, you would find something quite startling. Humans have less genetic variation than most other animal species, including many that we consider endangered. A population of chimpanzees living in a single forest in Africa contains more genetic diversity than the entire human species spread across the globe. Two mice living in the same field are likely to be more genetically different from each other than a human from Norway and a human from New Guinea. This pattern of low genetic diversity suggests that at some point in our recent evolutionary past, the human population was reduced to a very small number of individuals. Population geneticists call this phenomenon a genetic bottleneck, and the evidence suggests that the human bottleneck was severe enough to reduce our global population to perhaps as few as 1,000 breeding pairs. To put this in perspective, there are currently more endangered mountain gorillas in the wild than there were humans during this bottleneck period. The most likely cause of this near extinction was the eruption of Mount Toba in Sumatra, roughly 74,000 years ago, an event so catastrophic that it changed the climate of the entire planet and created what scientists call a volcanic winter that lasted for years. To understand the scale of this eruption, consider that it ejected roughly 2,800 cubic kilometers of rock and ash into the atmosphere. For comparison, the eruption of Mount Vesuvius that destroyed Pompeii ejected about 3 cubic kilometers of material. The eruption of Mount St. Helens in 1980 ejected about 1 cubic kilometer. The Toba eruption was roughly 1,000 times larger than Mount St. Helens and nearly 1,000 times larger than Vesuvius. When Toba erupted, it sent enormous quantities of volcanic ash and sulfur dioxide high into the atmosphere, where they spread around the globe and blocked sunlight for years. Global temperatures dropped by several degrees, creating conditions similar to a nuclear winter. Plants died from lack of sunlight, ecosystems collapsed, and animal populations crashed worldwide. For early humans living in small, scattered populations across Africa and parts of Asia, this would have been an existential crisis. Food sources disappeared as plants died and animals fled or perished. Water sources became contaminated with volcanic ash. The air itself became difficult to breathe in areas where ashfall was heavy. Archaeological evidence suggests that human populations crashed during this period. Tool-making traditions that had existed for thousands of years disappeared, suggesting that the knowledge needed to create them was lost when the people who possessed that knowledge died. Genetic evidence suggests that many human populations went extinct entirely, leaving no descendants in the modern gene pool. The humans who survived this catastrophe were probably concentrated in a few refugia, areas where local conditions were slightly more favourable for survival. These refugia may have been in parts of Africa that were less affected by the volcanic winter, or perhaps in coastal areas where marine food sources remained available when terrestrial ecosystems collapsed. From these tiny surviving populations, all of modern humanity is descended. Every person alive today can trace their ancestry back to the few thousand individuals who survived the Toba eruption and the climate catastrophe that followed. This shared ancestry helps explain why human genetic diversity is so limited compared to other species. But the Toba bottleneck may not have been the only near-extinction event in human history. Genetic evidence suggests that human populations experienced several periods of severe reduction, creating a pattern of bottlenecks and recoveries that shaped our evolutionary trajectory in profound ways. Earlier bottlenecks may have occurred when human populations first migrated out of Africa, encountering new diseases, climates, and environmental challenges that reduced their numbers to small groups of survivors. Each successful migration to a new continent or island would have involved a founder effect, where a small group of colonizers established a new population with reduced genetic diversity compared to the source population. The migration to Australia roughly 50,000 years ago probably involved fewer than 1,000 individuals crossing the water barriers between Southeast Asia and the Australian continent. The colonization of the Americas, whether it occurred 15,000 years ago or earlier, probably involved even smaller founding populations crossing the Bering Land Bridge or travelling along Pacific coastlines. Each of these migration events created genetic bottlenecks that reduced human diversity and shaped the characteristics of regional populations. The genetic differences between modern human populations largely reflect these ancient founder effects and the evolutionary changes that occurred in isolated populations after they separated from their source groups. The consequences of these bottlenecks extend far beyond simple genetic diversity. Population bottlenecks tend to amplify the effects of genetic drift, random changes in gene frequencies that can occur when populations are small. In large populations, genetic drift has minimal effects because random changes in one part of the population are balanced by opposite changes elsewhere. In small populations, genetic drift can cause significant changes in gene frequencies and can even lead to the loss of beneficial genetic variants. This means that some of the characteristics that distinguish modern humans from other animals may be partly the result of genetic drift during bottleneck periods, rather than natural selection for advantageous traits. Some human features that we consider adaptive may actually be neutral traits that became common in human populations simply because they happened to be present in the small groups that survived bottleneck events. The bottlenecks in human evolutionary history also help explain some puzzling aspects of human genetics. For example, humans have an unusual number of genetic variants that cause diseases when present in 2 copies but may provide advantages when present in only 1 copy. Sickle cell anemia, Tay-Sachs disease, and cystic fibrosis are all examples of genetic variants that persist in human populations despite their harmful effects when inherited from both parents. These disease-causing variants probably persist because they provided survival advantages during specific environmental challenges that human populations faced in the past. Sickle cell trait provides resistance to malaria, which may have been crucial for survival in malarial environments. Tay-Sachs trait may provide resistance to tuberculosis. Cystic fibrosis trait may provide resistance to cholera or typhoid fever. During population bottlenecks, when survival was marginal and disease outbreaks could eliminate entire communities, genetic variants that provided even small advantages against specific diseases could make the difference between survival and extinction. Populations that survived bottlenecks may have been those that happened to carry genetic variants that protected them from the particular diseases or environmental challenges they faced. The genetic legacy of these bottlenecks also influences modern human health in ways we're still discovering. The limited genetic diversity that resulted from ancient population crashes means that humans are more vulnerable to certain types of diseases than species with greater genetic diversity. Genetic diseases that are rare in other animals are relatively common in humans, because our limited gene pool makes it more likely that individuals will inherit harmful variants from both parents. On the other hand, the genetic uniformity of human populations has made it easier for humans to share medical knowledge and treatments across different groups. A medication that works for one human population is likely to work for others because the underlying biology is similar. This genetic similarity has facilitated the development of global health initiatives and medical interventions that can benefit the entire species. The population bottlenecks in human history also influenced the development of human culture and social behavior. Small populations surviving in challenging environments would have needed extraordinary levels of cooperation and knowledge sharing to survive. The sophisticated social behaviors that characterize modern humans, including language, complex tool-making, and cooperative child-rearing, may have evolved partly in response to the survival challenges posed by living in small, vulnerable populations. During bottleneck periods, every individual would have been crucial for group survival. The loss of any adult would have deprived the group of essential knowledge and skills needed for finding food, making tools, or navigating environmental challenges. This would have created strong selection pressure for cultural mechanisms that ensured knowledge was shared and preserved across generations. Language in particular would have been essential for survival during bottleneck periods. The ability to communicate complex information about food sources, tool-making techniques, and environmental hazards would have been crucial for small groups trying to survive in challenging conditions. Groups with better communication abilities would have been more likely to survive and reproduce, gradually improving human linguistic capabilities. The extended childhood that characterizes modern humans may also reflect adaptations to bottleneck conditions. In small populations where every individual possesses crucial survival knowledge, it becomes essential to invest heavily in training the next generation. A long childhood provides time for young humans to learn the complex skills and knowledge needed for survival, ensuring that essential information isn't lost when older group members die. The cooperative breeding behaviors that distinguish humans from other primates may also have evolved in response to bottleneck conditions. When populations are small and every individual is essential for group survival, it becomes advantageous for all group members to help care for children, not just the biological parents. This shared investment in child rearing increases the likelihood that children will survive to adulthood and reproduce, helping the population recover from bottleneck conditions. Interestingly, some scientists have suggested that humans are still experiencing the effects of ancient bottlenecks in our modern social behavior. The tendency for humans to form close-knit groups of roughly 100 to 150 individuals may reflect the optimal group size for survival during bottleneck periods. This number, known as Dunbar's number, appears to represent the maximum number of stable social relationships that humans can maintain simultaneously. Modern humans often feel most comfortable in social groups that are similar in size to the small populations that survived ancient bottlenecks. We form tribes, communities, and organizations that rarely exceed a few hundred individuals before splitting into smaller subgroups. This may reflect ancient psychological adaptations to living in small populations where everyone knew everyone else and group cohesion was essential for survival. The experience of surviving population bottlenecks may also have influenced human psychology in other ways. The anxiety and stress responses that characterize modern humans may be partly evolutionary adaptations to living in small populations where any threat could potentially eliminate the entire group. The tendency for humans to worry about low probability but high impact risks may reflect the psychological legacy of ancestors who survived by being constantly vigilant about potential catastrophes. Human risk assessment often seems irrational from a statistical perspective. We worry more about airplane crashes than car accidents, despite the fact that driving is statistically much more dangerous than flying. We fear terrorism more than heart disease, despite the fact that heart disease kills far more people. This pattern of risk perception may reflect ancient psychological mechanisms that evolved to help small populations avoid extinction by being extremely cautious about any threat that could potentially eliminate the entire group. The bottlenecks in human evolutionary history also provide perspective on our current situation as a species. Modern humans number in the billions and occupy every continent except Antarctica. We have technologies that allow us to survive in environments that would have been impossible for our ancestors. We have global communication networks that ensure knowledge can be preserved and shared even if local populations are eliminated. Yet we also face challenges that are similar in some ways to those faced by our ancestors during bottleneck periods. Climate change, environmental degradation, and the potential for nuclear warfare all represent threats that could potentially cause severe population crashes or even human extinction. The same vulnerabilities that nearly eliminated our species in the past could potentially threaten us again in the future. The genetic evidence of ancient bottlenecks serves as a reminder that human survival is not guaranteed and that our current success as a species doesn't protect us from future challenges. The fact that we survived previous near-extinction events doesn't mean we're immune to similar threats in the future. But the story of human bottlenecks is also a story of resilience and recovery. Despite facing environmental catastrophes that eliminated many other species, small human populations managed to survive, adapt, and eventually thrive. The cultural and genetic innovations that allowed our ancestors to survive bottleneck periods continue to serve us well as we face modern challenges. The Great Brain Gamble, trading jaws for intelligence. As you settle more deeply into the quiet rhythm of the night, let's explore perhaps the most audacious gamble in all of evolutionary history, the decision your ancestors made, if you can call it a decision, to trade the powerful jaws and robust skulls that had served primates well for millions of years in exchange for something unprecedented, a skull that could house an enormous, energy-hungry brain. It sounds like a reasonable trade-off when described that way, doesn't it? Give up some jaw strength to gain intelligence. But when you examine the details of this evolutionary bargain, it becomes clear just how risky and improbable it really was. Your ancestors essentially bet their species' survival on the possibility that a larger brain would provide advantages that outweighed the enormous costs and vulnerabilities that came with it. To understand the magnitude of this gamble, we need to appreciate what your ape-like ancestors were giving up. Early hominins had skulls that were masterpieces of mechanical engineering, designed to generate and withstand enormous bite forces. Their jaws were powered by massive muscles that attached to prominent ridges on their skulls, creating a system capable of cracking nuts, crushing tough plant fibers, and processing foods that would challenge even modern industrial machinery. These weren't just powerful jaws, they were precisely engineered systems for extracting nutrients from challenging food sources. The teeth were thick and robust, with complex surfaces for grinding tough plant material. The jaw joints were positioned to maximize mechanical advantage. The skull itself was built like a fortress, with thick bone and reinforcing ridges that could withstand the enormous stresses generated by powerful chewing muscles. This cranial architecture had been perfected over millions of years of primate evolution. It was a proven system that allowed our relatives to thrive in diverse environments by processing a wide variety of foods efficiently. Gorillas today can crack nuts that would challenge a hammer. Chimpanzees can strip bark from trees and chew through tough roots that humans couldn't begin to process without tools. But this robust skull design came with a constraint. The massive jaw muscles required large attachment areas on the skull, which limited the space available for brain tissue. The sagittal crest, a prominent ridge running along the top of the skull in many primates, provides attachment area for jaw muscles but leaves little room for brain expansion underneath. Somewhere in our evolutionary past, this trade-off began to shift. Rather than continuing to invest in jaw strength and processing power, human ancestors began to invest in brain size. This required a fundamental redesign of the skull, weakening the jaw system to make room for neural tissue. The first step in this transformation was probably the loss of the sagittal crest. As this ridge became smaller and eventually disappeared, the jaw muscles became weaker, but space became available for brain expansion. The skull could become more rounded and dome-like rather than elongated and reinforced for jaw muscle attachment. But removing the sagittal crest was just the beginning. To make significant room for brain expansion, the entire facial architecture had to be reorganized. The face became smaller and more delicate. The teeth became smaller and less robust. The jaw itself became shorter and weaker. What emerged was a skull design that prioritized brain space over jaw strength. From an engineering perspective, this transformation was dramatic. Imagine if someone took a Formula One race car designed for maximum performance and efficiency and converted it into a mobile library, sacrificing speed and power for the ability to carry as many books as possible. That's roughly analogous to what happened to the human skull during the transition from powerful-jawed early hominins to large-brained modern humans. The consequences of this transformation were immediate and severe. Weakened jaws meant that foods that had been dietary staples for millions of years became impossible to process. Early humans could no longer crack hard nuts with their teeth. They couldn't strip bark from trees or chew through tough roots. They couldn't even process raw meat efficiently without tools to help them. This created what scientists call the cooking hypothesis, one of the most elegant explanations for how early humans survived the transition to weaker jaws and smaller teeth. According to this hypothesis, humans compensated for their reduced ability to process food mechanically by learning to process it thermally, using fire to break down tough plant fibers and animal proteins before consuming them. Cooking essentially moves digestion outside the body, using heat to begin the process of breaking down nutrients before they enter the digestive system. Cooked food is easier to chew, easier to swallow, and easier to digest, allowing humans with weak jaws and small teeth to extract nutrients efficiently from foods that would be impossible to process raw. The cooking hypothesis suggests that the control of fire and the evolution of large brains were intimately connected. As early humans became increasingly dependent on cooked food, they needed the intelligence to maintain fires, plan cooking activities, and coordinate the complex social behaviors required for food preparation and sharing. This created a positive feedback loop between brain size and cultural complexity. Larger brains enabled more sophisticated tool use and food processing techniques, which made it possible to extract more nutrients from the environment, which could support even larger brains, which enabled even more sophisticated cultural behaviors. But cooking wasn't the only innovation that made the big brain gamble possible. Early humans also had to develop entirely new ways of acquiring and processing food. They became hunters and scavengers, using tools to kill animals and extract nutrients from carcasses. They developed techniques for processing plant foods, grinding seeds and roots with stone tools to make them more digestible. These technological innovations required not just intelligence, but also sophisticated social cooperation. Hunting large animals required coordinated group action. Processing and sharing food required complex social rules and communication systems. Maintaining fires and tools required division of labor and knowledge sharing across generations. The brain expansion that made these innovations possible came with enormous metabolic costs. Brain tissue is metabolically expensive, requiring roughly 20 times more energy per gram than muscle tissue. A human brain at rest consumes about 20% of the body's total energy production, compared to roughly 8% for the brains of other primates. This metabolic demand means that humans require a constant supply of high-quality nutrients to keep their brains functioning properly. Unlike other animals, which can survive for extended periods on low-quality food sources, humans begin experiencing cognitive impairment within hours of inadequate nutrition. Severe malnutrition can cause permanent brain damage in ways that don't affect other organs as dramatically. The energy demands of large brains also influenced other aspects of human anatomy and physiology. To free up energy for brain function, humans had to economize elsewhere. Human digestive systems became smaller and less robust compared to other primates, requiring us to consume higher quality, more easily digestible foods. Human muscle mass is also relatively small compared to other primates of similar size. While a chimpanzee is roughly 5 times stronger than a human of similar weight, humans have much larger brains relative to body size. This represents a fundamental trade-off between physical strength and cognitive ability. The reproductive costs of large brains were perhaps even more significant than the metabolic costs. Large brains require large skulls, which creates serious problems during childbirth. The human birth canal had to be a compromise between the pelvic anatomy needed for efficient bipedal locomotion and the space needed for large-skulled babies to pass through during birth. This compromise resulted in what scientists call the obstetrical dilemma. Human babies must be born with skulls that are small enough to fit through the birth canal, which means they're born in a remarkably underdeveloped state compared to other mammals. Human babies are essentially born prematurely, with brains that are only about 25% of adult size. This creates an extended period of postnatal brain development during which human infants are completely helpless and dependent on adult care. While most mammalian young can walk and feed themselves within hours or days of birth, human infants require months to achieve basic motor skills and years to achieve independence. The extended period of infant dependency created new challenges for early human societies. Adult humans had to invest enormous amounts of time and energy in childcare, reducing the time available for food acquisition and other survival activities. This made it essential for human groups to develop cooperative breeding systems where multiple adults shared responsibility for raising children. The cooperative breeding required for raising large-brained, helpless infants probably drove the evolution of many uniquely human social behaviors. Pair bonding between males and females became advantageous because it ensured that both parents would invest in childcare. Extended family networks became important for providing additional support during the long period of child dependency. Language probably evolved partly in response to the communication needs created by cooperative child rearing and the complex social coordination required to support large-brained infants. The ability to share information about childcare, coordinate food sharing, and maintain social relationships across extended family networks would have been crucial for successful reproduction. The timing of brain development in humans also influenced human learning and culture in profound ways. Because so much brain development occurs after birth, human children's brains are shaped extensively by their environment and experiences. This creates what scientists call phenotypic plasticity, the ability for the same genetic blueprint to produce different outcomes depending on environmental conditions. Yep, human children are essentially born with brains that are designed to be programmed by their culture. Unlike other animals, which are born with most of their behavioral patterns already established, human children must learn virtually everything they need to know for survival through cultural transmission from their parents and community. This cultural programming happens during what researchers call critical periods, specific times during development when the brain is particularly receptive to certain types of learning. The critical period for language acquisition, for example, occurs during the first few years of life, when children can effortlessly learn multiple languages with perfect pronunciation and grammar. Adults attempting to learn new languages must work much harder to achieve far less fluent results. The extended period of brain development and cultural learning created what anthropologists call the human cultural niche. Humans became the first species to survive primarily through cultural adaptation rather than biological adaptation. Instead of evolving different physical characteristics to survive in different environments, humans developed different cultural practices, technologies, and knowledge systems. This cultural adaptation could happen much faster than biological evolution. While genetic changes take many generations to spread through populations, cultural innovations can spread within a single generation. A useful tool or technique discovered by one individual can be learned and adopted by others within months or years, rather than requiring the thousands of years needed for genetic changes. The speed of cultural evolution meant that human populations could adapt to new environments and challenges much more rapidly than other species. When humans migrated to new continents and encountered unfamiliar climates, foods, and predators, they could develop appropriate technologies and survival strategies within a few generations rather than waiting for natural selection to produce genetic adaptations. But the reliance on cultural adaptation also created new vulnerabilities. Cultural knowledge could be lost much more easily than genetic information. If the individuals who possessed crucial survival knowledge died before passing it on to the next generation, entire populations could lose essential technologies and skills. This vulnerability to cultural loss probably influenced the evolution of human social behaviors related to teaching and learning. Humans developed elaborate systems for ensuring that important knowledge was preserved and transmitted across generations. Rituals, stories, songs, and formal teaching practices all serve to embed crucial survival information in cultural contexts that make it more likely to be remembered and passed on. The evolution of language was probably crucial for reliable cultural transmission. While other animals can learn by observation and imitation, language allows humans to share abstract concepts, explain the reasoning behind techniques, and pass on knowledge about events and situations that aren't immediately present. Language also allowed humans to engage in collaborative reasoning, combining the knowledge and insights of multiple individuals to solve problems that no single person could solve alone. This collective intelligence became one of humanity's greatest advantages, allowing human groups to tackle challenges that would overwhelm any individual. The brain expansion that made language and cultural transmission possible also enabled other uniquely human cognitive abilities. Humans developed the capacity for abstract reasoning, allowing them to think about concepts that have no direct physical reference. Mathematical thinking, moral reasoning, artistic creativity, and spiritual contemplation all depend on this ability to manipulate abstract concepts mentally. Humans also developed sophisticated abilities for mental time travel, the capacity to remember past events in detail and imagine future scenarios with considerable complexity. This temporal reasoning allows humans to learn from history, plan for the future, and make decisions based on long-term consequences rather than immediate rewards. The capacity for mental simulation, imagining hypothetical scenarios and their likely outcomes, became crucial for human survival and success. Humans could test ideas mentally before implementing them physically, reducing the risks associated with trial and error learning. A hunter could imagine different stalking strategies and choose the most promising one without alerting prey through failed attempts. These advanced cognitive abilities came with their own costs and limitations. The human capacity for abstract reasoning and mental time travel also enables uniquely human forms of suffering. Humans can worry about future events that may never occur, feel guilt about past actions, and experience existential anxiety about abstract concepts like death and meaninglessness. The same cognitive abilities that allow humans to plan for the future and learn from the past also make humans capable of depression, anxiety, and other mental health conditions that appear to be rare or absent in other animals. The price of sophisticated consciousness may be vulnerability, to forms of psychological suffering that simpler minds cannot experience. The evolution of large brains also influenced human social structure in ways that continue to shape modern societies. Large-brained infants require intensive care for extended periods, which favoured the evolution of complex kinship systems and social support networks. Human societies developed elaborate rules for determining who was responsible for caring for children and how resources should be shared among family members. The need to coordinate complex social behaviours also drove the evolution of sophisticated social cognition. Humans developed the ability to understand the mental states of other individuals, to predict their behaviour based on their beliefs and desires, and to manipulate social situations through strategic communication. This social intelligence became as important as technical intelligence for human survival. Success in human societies depends not just on the ability to solve practical problems, but also on the ability to navigate complex social relationships, form alliances, negotiate conflicts, and maintain one's reputation within the group. The combination of technical intelligence and social intelligence created what some researchers call the human cognitive niche. Humans became the species that survives through collective intelligence, combining the knowledge and skills of many individuals to solve problems and adapt to challenges that would overwhelm any single person. This collective intelligence is evident in even the simplest human technologies. A stone axe might seem like a simple tool, but creating one requires knowledge of geology to find appropriate stones, understanding of physics to shape them effectively, and social coordination to learn the techniques from others and pass them on to future generations. More complex technologies like agriculture, metallurgy, and writing systems represent the accumulated knowledge of thousands of individuals working across many generations. No single person could reinvent agriculture from scratch, but human societies collectively developed and refined agricultural techniques over thousands of years, gradually transforming human civilization. The brain expansion that made collective intelligence possible also changed the relationship between humans and their environment. While other species adapt to their environments through genetic changes, humans began adapting their environments to meet their needs. Instead of evolving thicker fur to survive cold climates, humans learned to make clothing and shelters. Instead of evolving larger teeth to process tough foods, humans learned to cook and use tools for food preparation. This environmental manipulation gradually transformed human ecological impact from that of a typical large mammal to something unprecedented in Earth's history. Humans became ecosystem engineers, deliberately modifying landscapes to support larger populations and more complex societies. The agricultural revolution, which began roughly 10,000 years ago, represented the full flowering of the big brain gamble. Human intelligence had reached the point where it could support population densities and social complexities that would have been impossible for any other animal of similar size. But agriculture also revealed some of the limitations and trade-offs associated with human brain evolution. Agricultural societies could support larger populations, but they also created new forms of inequality, conflict, and environmental degradation. The same intelligence that allowed humans to manipulate their environment also created problems that required ever more sophisticated solutions. The modern world represents both the triumph and the ongoing challenge of the big brain gamble. Human intelligence has created technologies that would seem magical to our ancestors, technologies that allow us to communicate instantly across vast distances, travel to other planets, and manipulate matter at the atomic level. Yet we also face challenges that our evolved cognitive abilities are poorly equipped to handle. Climate change, nuclear weapons, artificial intelligence, and global economic systems all represent problems that require thinking about complex systems, long-term consequences, and statistical relationships that human brains find difficult to process intuitively. The big brain gamble that began millions of years ago with the first enlargement of human cranial capacity continues today as we try to use Stone Age minds to solve space-age problems. The same cognitive abilities that allowed our ancestors to survive in small groups on the African savanna must now grapple with global challenges that affect billions of people across multiple generations. The evolutionary history of human brain expansion also provides perspective on contemporary debates about intelligence, consciousness, and artificial intelligence. Human intelligence is not a single unified capacity, but rather a collection of specialized cognitive abilities that evolved to solve specific problems faced by our ancestors. Understanding the evolutionary origins of human intelligence can help us appreciate both its remarkable capabilities and its inherent limitations. We are not rational calculating machines, but evolved organisms whose thinking is shaped by millions of years of natural selection for survival and reproduction in small social groups. This evolutionary perspective also suggests that human intelligence is not the pinnacle of possible cognitive evolution, but rather one particular solution to the challenges of survival and reproduction. Other forms of intelligence, whether they evolve naturally in other species or are created artificially by humans, might have very different characteristics and capabilities. The story of human brain evolution also illustrates the fundamental unpredictability of evolutionary processes. The big brain gamble could easily have failed, leaving humans as a minor branch of the primate family tree with slightly larger brains, but no particular evolutionary success. The fact that it succeeded reflects not the inevitability of human intelligence, but rather the fortunate alignment of environmental challenges, genetic variations, and cultural innovations that made large brains advantageous despite their enormous costs. A slightly different sequence of environmental changes or genetic mutations could have led to very different outcomes. As you lie there tonight, your brain cycling through its nightly maintenance routines, you're participating in the ongoing experiment that began millions of years ago when your ancestors first traded jaw strength for neural capacity. Every thought you think, every memory you form, every problem you solve represents a continuation of the most audacious gamble in evolutionary history. The 3 pounds of neural tissue in your skull consume roughly 400 calories per day, about the same amount of energy that a small mammal needs for its entire daily metabolism. This energy expenditure would have been prohibitively expensive for your ancestors if they hadn't developed the cultural innovations that made high-quality nutrition consistently available. Your brain contains roughly 86 billion neurons, each connected to thousands of others through synapses that number in the trillions. This neural network is more complex than any other known structure in the universe, capable of generating consciousness, creativity, love, and understanding in ways that we're still struggling to comprehend. Yet this remarkable organ is also fragile and vulnerable in ways that reflect its evolutionary history. Your brain cannot survive more than a few minutes without oxygen, cannot function properly without a constant supply of glucose, and can be permanently damaged by toxins, diseases, or physical trauma that other organs might easily survive. The evolutionary trade-offs that created your brain also influence your daily experience in subtle but important ways. Your need for high-quality nutrition means you cannot survive on the simple plant diets that sustain other primates. Your extended childhood means you required years of intensive care to reach maturity. Your sophisticated social cognition makes you vulnerable to forms of psychological distress that simpler minds cannot experience. Most private and individual of experiences, you're not alone. Your consciousness is participating in something larger, touching the same archetypal patterns that have guided and inspired human beings for millennia. Your dreams connect you not just to your own deeper wisdom, but to the collective wisdom of your entire species. But let's delve even deeper into the mystery of where consciousness goes during sleep, by exploring what happens during those rare but profound experiences that some people report of encountering deceased loved ones in dreams. These visitation dreams, as they're sometimes called, often feel qualitatively different from ordinary dreams, carrying a sense of reality and significance that can be life-changing for those who experience them. People who have visitation dreams often describe them as feeling more real than reality itself. The deceased person appears healthy and radiant, communicates important messages, provides comfort or guidance, and leaves the dreamer with an unshakable sense that they've had a genuine encounter rather than just a dream. These experiences can bring profound healing, closure, and peace to those who are grieving. From a conventional perspective, visitation dreams are understood as the psyche's way of processing grief and loss. The mind creates these vivid encounters as a way of working through emotions, providing comfort and gradually adapting to the reality of separation. The brain's remarkable capacity for creating realistic simulations allows it to generate experiences that feel completely real and meaningful to the dreamer. Yet the consistency and power of these experiences across different cultures and belief systems suggests that something significant is happening, regardless of whether we interpret it as literal contact with deceased consciousness or as a profound healing process generated by the dreaming mind. Either way, these experiences point to the extraordinary capacity of sleeping consciousness to generate encounters that transcend the normal boundaries of space, time, and physical reality. If consciousness during sleep can create such vivid and meaningful encounters with people who are no longer physically present, what does that tell us about the nature of consciousness itself? It suggests that awareness might not be as dependent on physical brains as we typically assume, or at least that consciousness can create experiences that feel completely independent of physical limitations. These visitation dreams also raise profound questions about the continuity of consciousness and identity. If you can encounter your deceased grandmother in a dream and have a conversation that feels completely real and brings you genuine comfort and insight, what does that say about the nature of her consciousness and yours? Are these encounters evidence that consciousness survives bodily death? Or are they evidence that consciousness is so creative and multidimensional that it can generate experiences that transcend any normal understanding of what's possible? Perhaps the answer doesn't matter as much as the experiences themselves. Whether visitation dreams represent literal contact with deceased consciousness or the miraculous healing capacity of the sleeping mind, they demonstrate that consciousness during sleep can access realms of meaning and connection that far exceed what seems possible from a purely materialistic perspective. Now, as we continue our gentle journey through the peculiarities of human evolution, we arrive at perhaps one of the most extraordinary developments in our species' story: the emergence of something that sets us apart from every other creature that has ever walked, crawled, swum, or flown across this planet. We're speaking, of course, about the spark of symbolic language, that remarkable ability to take the chaotic swirl of thoughts in our minds and transform them into patterns of sound and meaning that can leap from one consciousness to another, carrying with them not just information, but emotion, imagination, and the very essence of what it means to be human. The question of how and why symbolic language emerged is one that has puzzled scientists for generations, and it's the kind of mystery that reveals just how strange our evolutionary path truly is. Other animals communicate, certainly. They warn of predators, attract mates, and coordinate group activities through an impressive array of calls, gestures, and chemical signals. But human language is something altogether different, something that seems to have appeared relatively suddenly in evolutionary terms, like a firework exploding in the darkness of our past, illuminating everything that came after with its brilliant transformative light. Think about what you're doing right now as you listen to these words. Somehow, the electrical patterns in my brain when I formed these thoughts have been translated into sound waves, which your ears have captured and your brain has decoded back into meaning. Even more remarkably, these aren't just simple signals like danger or food, but complex abstract concepts that can refer to things that don't exist, events that haven't happened, and ideas that exist only in the realm of imagination. This is the magic of symbolic language, and it's so fundamental to who we are that we rarely pause to consider just how extraordinary it really is. The theories about how this linguistic spark ignited in our ancestors are as varied and fascinating as the phenomenon itself. Some researchers, following what's often called the gossip hypothesis, suggest that language evolved as a way for our increasingly social ancestors to share information about who was trustworthy, who was dangerous, and who was worth forming alliances with. In this view, language began as a kind of social grooming, a way to build and maintain the complex relationships that were becoming essential for survival in larger and larger groups. Imagine our early ancestors, perhaps 200,000 years ago, sitting around fires in the evening, their days filled with the challenges of finding food, avoiding predators, and navigating the intricate social dynamics of group life. As their brains grew larger and their social groups became more complex, the simple grunts and gestures that had served their predecessors were no longer sufficient. They needed a way to share more detailed information, to warn about the unpredictable behavior of that hunter from the neighboring group, to coordinate complex plans for the next day's foraging expedition, to build the trust and understanding that would hold their community together. This social grooming function of early language makes sense when we consider how much of our modern conversations still serves similar purposes. We chat about the weather not because meteorology is particularly fascinating, but because it's a safe way to establish connection. We share stories about mutual acquaintances, discuss the events of our day, and engage in the countless small exchanges that weave the fabric of our social bonds. Even now, as you listen to these words, we're engaged in a kind of one-sided social grooming, building a temporary connection across time and space through the medium of language. But there's another theory about language origins that's equally compelling, one that suggests our capacity for symbolic communication might have emerged from something even more fundamental to human experience: music. The parent-infant interaction hypothesis proposes that the proto-language of our ancestors might have been more like song than speech, emerging from the melodic babbling between mothers and their babies, those tender exchanges of coos and gurgles and rhythmic sounds that still form the foundation of how we bond with our young. Consider how naturally music and language intertwine in human experience. When we're trying to soothe a crying baby, we don't speak in flat, monotone sentences. We instinctively raise our pitch, exaggerate our intonation, and create melodic patterns that seem to bypass rational thought and speak directly to some deeper part of the infant's developing consciousness. Lullabies exist in every culture on Earth, suggesting that this musical dimension of communication is truly universal, something that emerged so early in our evolution that it became woven into the very fabric of what makes us human. The relationship between music and language runs even deeper than these surface similarities might suggest. Both involve the precise timing of sounds, the creation of patterns that unfold over time, and the ability to convey emotion and meaning through abstract symbols. When we listen to a sad song, our brains respond as if we're experiencing actual sadness, even though we know intellectually that we're just hearing organized sound waves. This suggests that music and language might tap into the same fundamental neural pathways, the same cognitive machinery that allows us to find meaning in pattern and significance in sound. Some researchers have even proposed that our ancestors might have passed through a stage of evolution they call proto-musical, where communication was more like singing than speaking, where information was embedded in melody and rhythm rather than in discrete words and grammatical structures. This would explain why human infants are born with such an extraordinary sensitivity to musical patterns, why they can distinguish between different rhythmic structures before they can even crawl, and why musical training seems to enhance language development in ways that go far beyond simple pattern recognition. There's something deeply moving about imagining our ancestors communicating through song, their voices rising and falling around evening fires, weaving together individual melodies into harmonies that bound the group together in ways that simple speech never could. In this vision of early human communication, language didn't emerge from the need to convey information efficiently, but from the desire to share emotional states, to create collective experiences that transcended individual consciousness. But perhaps the most intriguing theory about language origins is one that takes us into even stranger territory, into the realm of altered consciousness and mystical experience. Some researchers have suggested that symbolic language might have emerged from shamanic practices, from the altered states of consciousness that our ancestors entered through meditation, rhythmic dancing, fasting, or the consumption of psychoactive plants. In these altered states, they argue, early humans might have experienced their first glimpses of truly symbolic thought, the ability to see meaning in metaphor, to understand that one thing could represent another in ways that transcended simple mimicry. This shamanic hypothesis is compelling because it addresses one of the most puzzling aspects of human language, its fundamentally symbolic nature. While other animals can learn to associate specific sounds with specific objects or actions, human language depends on the understanding that sounds are symbols, that they refer to things rather than simply being triggered by them. This is a cognitive leap that seems almost impossibly sophisticated, the kind of insight that might require a fundamentally different kind of consciousness than anything we see in other species. In altered states of consciousness, whether induced by substances, sensory deprivation, or intense meditation, people often report experiences that are fundamentally symbolic, visions where objects and events take on meanings that extend far beyond their literal significance. A tree might represent the connection between earth and sky. A serpent might embody the cycle of death and rebirth. A journey through a dark cave might symbolize the passage from ignorance to enlightenment. These experiences suggest that symbolic thinking might be most accessible to consciousness when it's freed from the constraints of ordinary practical awareness. If this theory is correct, then language might have originated not in the mundane exchanges of daily life, but in the profound altered states that allowed our ancestors to glimpse the symbolic nature of reality itself. The shamans of early human communities, those individuals who specialized in entering and navigating these altered states, might have been the first to develop truly symbolic communication, using their visions and insights to create new ways of thinking and speaking that gradually spread throughout their communities. This would explain why so many human cultures have traditions of shamanic healing, vision quests, and mystical practices that seem to unlock forms of consciousness unavailable in ordinary waking life. It might also explain why psychoactive substances have played such a persistent role in human culture, why nearly every society has discovered and used plants or fungi that alter consciousness in ways that seem to reveal hidden dimensions of meaning and connection. The idea that language might have emerged from mystical experience also resonates with the strange, almost magical quality that symbolic communication still possesses. When we read a powerful poem or hear a moving speech, we often feel that something profound has been transmitted, something that goes beyond the mere meaning of the words themselves. This suggests that language might retain some connection to its possibly shamanic origins, that it still serves as a bridge between ordinary consciousness and deeper realms of meaning and significance. Of course, the true origin of human language probably involved elements from all of these theories. Social grooming, musical communication, and shamanic symbolism might all have contributed to the emergence of our species' unique capacity for symbolic thought and expression. The development of language was likely a gradual process that unfolded over tens of thousands of years, with different aspects emerging at different times and in different populations, eventually weaving together into the rich tapestry of human communication we know today. What makes this emergence so remarkable is not just its complexity, but its speed. While other evolutionary developments unfolded over millions of years, the transition from simple animal communication to full symbolic language seems to have occurred in a relatively brief window of evolutionary time. This suggests that once the basic cognitive foundations were in place, language development might have undergone a kind of runaway evolution, where each advance in communication ability created new selective pressures that favored even more sophisticated linguistic capabilities. The development of language also had profound effects on every other aspect of human evolution. Once our ancestors could share complex information symbolically, they could pass on knowledge that transcended individual experience, building collective wisdom that accumulated across generations. They could plan more complex hunting strategies, develop more sophisticated tools, and create the rich mythological and spiritual frameworks that gave meaning to their lives. Language also transformed the nature of human consciousness itself. Before symbolic communication, each individual mind was essentially isolated, able to share only the most basic information about immediate needs and dangers. With language, minds could connect in ways that were previously impossible, sharing not just information but perspectives, emotions, and abstract concepts. This created the possibility of collective intelligence, the ability of groups to solve problems and generate insights that no individual could achieve alone. But the emergence of language brings us to another crucial turning point in human evolution, one that might have been just as transformative as the development of symbolic communication itself. We're speaking of the mastery of fire, that remarkable achievement that allowed our ancestors to extend their active hours into the darkness, to transform their diets in ways that fed their growing brains, and to create the warm, safe spaces where their increasingly complex social and intellectual lives could flourish. The control of fire represents one of the most significant technological breakthroughs in human history, rivaling the development of agriculture, the invention of writing, or the discovery of electricity in its transformative impact on our species. Yet unlike these later innovations, fire mastery happened so long ago and left such subtle traces in the archaeological record that we're still piecing together the story of how and when our ancestors first learned to harness this elemental force. What we do know is that the controlled use of fire marked a fundamental shift in the relationship between humans and their environment. For millions of years, our ancestors had been subject to the same basic limitations as other animals, active during the day when light allowed them to see, retreating to safe shelters when darkness fell. Fire changed all of that, extending the useful hours of each day and creating the possibility of a rich nocturnal life that was impossible for any other species. Imagine what it must have been like for early humans to sit around a fire as darkness gathered around them. The familiar landscape of their daytime world transformed into something mysterious and unknown. The flickering light would have created dancing shadows that seemed almost alive, while the circle of warmth and illumination became a kind of temporary sanctuary in the vast darkness beyond. For the first time in the history of life on Earth, a species could extend its active consciousness deep into the night, creating opportunities for socializing, storytelling, and contemplation that had never existed before. This extension of active time into the dark hours might have been crucial for the development of human culture and intelligence. During the day, our ancestors were busy with the practical tasks of survival, foraging for food, avoiding predators, and moving from place to place. But around the evening fire, they had time for different kinds of activities. The relaxed conversations that built social bonds, the sharing of knowledge and stories that transmitted culture from one generation to the next, and the quiet contemplation that might have sparked new insights about the nature of their world. The mastery of fire also transformed human diet in ways that had profound implications for brain development. Cooking food makes nutrients more bioavailable and easier to digest, allowing our ancestors to extract more energy from their meals while spending less time and effort on the mechanical process of chewing and digestion. This was particularly important for plant foods, which often contain toxins or tough cellular structures that can only be broken down through cooking. But perhaps even more significantly, cooking meat allowed our ancestors to extract far more calories and nutrients from their protein sources. Raw meat is difficult to chew and digest, limiting how much nutrition early humans could obtain from their hunting efforts. Cooked meat, on the other hand, is tender, easily digestible, and provides concentrated nutrition that can fuel energy-intensive activities like brain growth and complex social behavior. Some researchers have argued that cooking was so crucial for human evolution that it fundamentally altered our anatomy and physiology. Our teeth became smaller because we no longer needed the powerful grinding molars required for processing raw plant materials. Our digestive systems became shorter and less energy intensive because cooked food didn't require the extensive processing needed for raw diets. And our brains began to grow larger, possibly because the improved nutrition from cooked food could support the enormous energy demands of increasingly complex neural tissue. This cooking hypothesis suggests that fire mastery might have been the key innovation that allowed human brain sizes to expand so dramatically over the last 2 million years. The human brain consumes about 20% of our total energy budget, an enormous investment that would be difficult to sustain without the concentrated nutrition that cooking provides. By unlocking the full nutritional potential of their food, early humans might have gained access to the energy resources needed to build and maintain the large, complex brains that define our species. The control of fire also had subtler but equally important effects on human evolution, particularly on our sleep patterns and the rhythm of daily life. Before fire, the onset of darkness would have triggered biological responses similar to those we see in other diurnal animals, a slowing of activity and preparation for sleep. With fire, humans could extend their active period well into the night, creating a unique daily rhythm that distinguished them from virtually every other species on the planet. This extension of waking hours into the dark period of the day might have been crucial for the development of human dreaming and imagination. Around the fire, freed from the immediate demands of survival, early humans had time to engage in the kind of relaxed, associative thinking that generates new ideas and connections. The flickering light and dancing shadows might have stimulated their visual imagination, while the safety of the fire circle allowed their minds to wander into the kind of creative territories that are difficult to explore when constant vigilance is required. Some researchers have suggested that this extended evening period around fires might have been when humans first began to develop the rich, mythological and spiritual traditions that characterize our species. In the mysterious world beyond the firelight, where familiar shapes became strange and unknown sounds carried on the night air, our ancestors might have begun to imagine the presence of spirits, gods, and other supernatural beings that would later populate their religious and mythological systems. The stories told around these ancient fires might have been the beginning of human literature, the first attempts to make sense of the world through narrative rather than direct experience. These early stories would have served multiple functions, entertaining the group during the long dark hours, transmitting important cultural knowledge from older to younger members, and providing frameworks for understanding the mysterious forces that shaped their world. Fire also created new opportunities for technological development. The heat of fires could be used to harden wooden tools, shape stone implements, and eventually work with metals. The light allowed for detailed work that would have been impossible in natural darkness, enabling the creation of more sophisticated tools and artifacts. And the controlled environment around fires provided safe spaces for experimentation with new technologies and techniques. But perhaps most importantly, fire created the first truly human spaces, areas that were defined not by natural features, but by human activity and intention. The circle of light around a fire became a kind of temporary architecture, a space that belonged to humans rather than to the natural world. This might have been the beginning of the human tendency to create modified environments, the impulse that would eventually lead to the construction of shelters, villages, cities, and all the complex built environments that characterize human civilization. The mastery of fire also affected human social organization in profound ways. Gathering around fires required cooperation and shared responsibility, as maintaining a fire through the night demanded constant attention and fuel gathering. This might have strengthened social bonds and encouraged the development of more complex group coordination. Fire also created opportunities for larger gatherings, as multiple family groups could share the warmth and light of a single large fire, leading to the kind of extended social interactions that build cultural traditions and exchange networks. These evening gatherings around fires might have been crucial for the development of human tunes and music and dance as well. The rhythmic crackling of burning wood provides a natural metronome, while the warm, relaxed atmosphere encourages the kind of synchronized activities that build group cohesion. Archaeological evidence suggests that some of the earliest human art was created in firelit caves, suggesting that the controlled use of fire might have been essential for the development of human artistic expression. The transformation of human sleep patterns through fire mastery might have had even deeper implications for the development of consciousness and dreaming. By staying awake later into the night, early humans would have experienced different sleep cycles than their ancestors, possibly spending more time in the light sleep stages where vivid dreaming occurs. This could have contributed to the rich dream life that characterizes human consciousness, and might have influenced the development of symbolic thinking and mythological imagination. In many ways, the mastery of fire represents the first truly transformative technology in human history, the first innovation that fundamentally altered not just what humans could do, but who they could become. It created new opportunities for social interaction, cultural development, technological innovation, and spiritual exploration. It provided the energy resources needed to support larger brains and more complex behavior, and it established the foundation for all the subsequent technological developments that would eventually lead to modern human civilization. The story of fire mastery also illustrates one of the most remarkable aspects of human evolution, the way in which cultural innovations could drive biological change. Unlike most evolutionary developments, which occur through random genetic mutations that are then selected for or against by environmental pressures, human cultural evolution created new environmental pressures that shaped our biological development. The use of fire didn't just change human behavior, it changed human anatomy, physiology, and neurology in ways that made us fundamentally different from our ancestors. This interplay between cultural and biological evolution would become increasingly important as human societies grew more complex. Technologies, social institutions, and cultural practices began to shape the evolutionary pressures acting on human populations, creating a feedback loop where biological changes enabled new cultural innovations, which in turn created new biological pressures. This process, sometimes called gene-culture coevolution, helps explain why human evolution has been so rapid and why our species has become so different from our closest relatives in such a relatively short period of time. The mastery of fire also brings us to one of the most fascinating aspects of human cultural evolution, the development of origin myths and creation stories that attempt to explain where we came from and how we acquired our unique characteristics. Every human culture has developed elaborate narratives about the origins of humanity, stories that often contain surprising echoes of actual evolutionary processes and historical events, even when they are expressed in supernatural or mythological terms. These ancient stories of origin are particularly relevant to our exploration of human evolutionary strangeness, because they often focus on the very same peculiarities that puzzle modern scientists. Why are humans so different from other animals? How did we acquire language, fire, and the other technologies that define our species? Why do we have such large brains and such complex social organizations? The answers provided by traditional origin myths are obviously very different from those offered by modern evolutionary science, but the questions they address are remarkably similar. Consider the prevalence of creation stories that describe humans being formed from clay or earth by divine beings. These narratives, found in cultures from Mesopotamia to Africa to the Americas, typically emphasize the special nature of human creation, the idea that humans were made through a deliberate, intentional process rather than arising naturally like other animals. While the scientific account of human evolution is obviously very different, it does support the intuition underlying these myths that human development was somehow special, that we evolved in ways and at speeds that distinguish us from other species. The biblical account of humans being formed from clay in the Garden of Eden, for example, emphasizes the special relationship between humans and their creator, the idea that humans were given unique capacities for language, moral reasoning, and spiritual awareness that set them apart from the rest of creation. The Mesopotamian epic of Gilgamesh describes humans being created from clay mixed with the blood of a slain god, giving them both earthly and divine natures. Similar stories appear in ancient Egyptian texts, where humans are formed from the tears of the sun god, and in African traditions where the first humans are sculpted from clay by ancestral spirits. These clay creation myths are fascinating not just for their widespread occurrence, but for their emphasis on the idea that humans required special intervention to acquire their distinctive characteristics. They suggest that our ancestors intuited something that modern science has confirmed, that human evolution involved processes and developments that were somehow different from the ordinary mechanisms of natural selection and gradual change that shaped other species. Other origin myths focus more specifically on the acquisition of particular human traits and technologies. Fire, as we've discussed, plays a crucial role in many of these stories, often described as a divine gift that had to be stolen from the gods or earned through heroic actions. The Greek myth of Prometheus, who stole fire from Zeus and gave it to humanity, is perhaps the most famous example, but similar stories appear in Native American traditions, where coyote or rabbit tricks the fire spirits into sharing their secret, and in African tales where spider or tortoise figures outwit the sky gods to bring fire to earth. These fire acquisition myths are particularly interesting because they often emphasize the transformative nature of fire mastery, the idea that gaining control over fire fundamentally changed what it meant to be human. In many versions, the acquisition of fire is described as the event that separated humans from animals, the moment when our ancestors became truly human rather than just another species of clever ape. This intuition about the transformative power of fire aligns remarkably well with what modern science tells us about the role of cooking and fire mastery in human evolution. Language acquisition myths are equally widespread and equally fascinating in their parallels to scientific understanding. The Tower of Babel story in the Judeo-Christian tradition describes an original universal language that was later fragmented into multiple tongues as punishment for human pride. Many other cultures have similar stories about an original perfect language that was lost or divided, suggesting a widespread intuition that language diversity might be a relatively recent development in human history. Interestingly, some linguistic evidence supports the idea that modern language diversity might indeed be relatively recent. Studies of language change and divergence suggest that most of the world's language families began diverging only 50 to 100,000 years ago, which would be consistent with the idea that earlier human populations might have shared more similar communication systems. While there was never literally a single universal human language, the rapid diversification of languages following human migrations out of Africa might have created the conditions that inspired myths about linguistic fragmentation. Some origin myths also focus on the development of human intelligence and consciousness, often describing these as gifts from divine beings or the result of consuming magical substances. The Mesopotamian myth of Adapa describes a human who gained wisdom by eating from the tree of knowledge, while many Native American traditions include stories about humans gaining consciousness through the intervention of animal spirits or by consuming sacred plants. These narratives often emphasize the idea that human consciousness is somehow different from ordinary animal awareness, that it required special intervention or transformation to achieve. The prevalence of stories about humans gaining intelligence or consciousness through consuming special substances is particularly intriguing in light of theories about the role of psychoactive plants in human evolution. Some researchers have proposed that the consumption of psilocybin mushrooms, cannabis, or other consciousness-altering plants might have played a role in the development of human cognitive abilities, particularly our capacity for symbolic thinking and creative problem-solving. While these theories remain controversial, they do provide an interesting parallel to the widespread mythological emphasis on consciousness-altering substances as sources of human wisdom and awareness. Perhaps most fascinating are the origin myths that describe humans as descendants of sky beings or visitors from other worlds. These stories, found in cultures as diverse as the ancient Sumerians, the Aboriginal Australians, and various Native American tribes, typically describe the first humans as having arrived on Earth from somewhere else, often bringing advanced knowledge and technologies with them. While these myths are obviously not literally true, they do reflect the same intuition that puzzles modern scientists: the sense that human development was somehow too rapid and too comprehensive to be explained by ordinary evolutionary processes. The Sumerian myths about the Anunnaki, for example, describe a race of advanced beings who came to Earth and created humans as workers or servants, giving them language, agriculture, and other technologies. Similar stories appear in Australian Aboriginal traditions about the sky heroes who shaped the landscape and taught humans how to live, and in Native American legends about star people who brought sacred knowledge to early human communities. While these stories are clearly mythological, they do address the real puzzle of how humans acquired so many sophisticated capabilities in such a relatively short period of evolutionary time. These sky-being myths have gained new attention in recent decades due to the popularity of ancient astronaut theories, the idea that Earth might actually have been visited by extraterrestrial beings in the distant past, and that these visits influenced human development. While mainstream science rejects these theories as unsupported speculation, they do raise interesting questions about the rapid pace of human evolution and the seemingly sudden appearance of advanced human capabilities in the archaeological record. The ancient astronaut hypothesis, popularized by writers like Erich von Däniken and Zechariah Sitchin, suggests that various ancient texts and archaeological sites contain evidence of extraterrestrial contact. Proponents point to images that might represent spacecraft or astronauts, to structures that seem too advanced for their time periods, and to mythological accounts that might be garbled memories of actual alien encounters. They argue that direct intervention by advanced extraterrestrial beings could explain the rapid development of human intelligence, language, and technology that seems so puzzling from a conventional evolutionary perspective. While the ancient astronaut hypothesis is not supported by scientific evidence and involves many logical leaps and unsupported assumptions, it does highlight some genuinely puzzling aspects of human evolution. The rapid increase in brain size over the last 2 million years, the sudden appearance of sophisticated tools and art, and the development of complex language and social organization do represent evolutionary developments that are difficult to explain through conventional mechanisms alone. However, there are several problems with the ancient astronaut explanation for these developments. First, there's no credible physical evidence for extraterrestrial visitation in the ancient past. While some archaeological artifacts and ancient texts have been interpreted as depicting spacecraft or astronauts, these interpretations are highly speculative and often involve reading modern concepts into ancient materials that can be explained more simply through conventional archaeological understanding. Second, the ancient astronaut hypothesis doesn't actually solve the puzzle of rapid human evolution, it just pushes the question back one level. If humans were modified or influenced by extraterrestrial beings, we still need to explain how those beings acquired their advanced capabilities. Unless we're willing to invoke an infinite regression of increasingly advanced alien species, we still need to account for the development of intelligence and technology through natural processes somewhere in the universe. Third, while human evolution has indeed been rapid by conventional evolutionary standards, it's not so rapid as to require supernatural or extraterrestrial intervention. The timescales involved in human brain evolution, while fast relative to other major evolutionary changes, are still measured in millions of years, providing plenty of time for natural selection and other evolutionary mechanisms to produce dramatic changes. More importantly, we're now beginning to understand some of the specific mechanisms that might explain the rapid pace of human evolution. Gene-culture coevolution, the feedback loop between cultural innovations and biological change, can accelerate evolutionary processes far beyond their normal pace. When cultural innovations create new selective pressures, populations can evolve rapidly to take advantage of new opportunities or adapt to new challenges. The development of cooking, for example, might have created strong selective pressure for smaller teeth and shorter digestive systems, since individuals who could efficiently process cooked food would have had significant advantages over those whose anatomy was still optimized for raw diets. Similarly, the emergence of complex social groups might have favored individuals with better communication skills, larger brains, and more sophisticated social intelligence. These gene-culture coevolution processes can produce what's called a positive feedback loop, where cultural innovations make biological adaptations possible, which in turn enable new cultural innovations, which create pressure for further biological adaptations. This kind of runaway evolution can produce rapid changes that might seem impossible under normal selective pressures, but which are perfectly explainable once we understand the mechanisms involved. The archaeological record also provides increasingly clear evidence for the gradual development of human capabilities over time, rather than the sudden appearance that might be expected if external intervention were involved. Stone tool technologies show clear developmental sequences, with simple tools gradually becoming more sophisticated over hundreds of thousands of years. Cave art appears first in simple forms and gradually becomes more complex and refined. Archaeological sites show evidence of increasingly sophisticated social organization, trade networks, and technological knowledge developing over long periods of time. Perhaps most importantly, genetic studies of human evolution show clear evidence of common descent with other primates, with no signs of the kind of genetic manipulation that might be expected if extraterrestrial intervention had occurred. Human DNA shows exactly the patterns we would expect from natural evolutionary processes, with clear relationships to other ape species and gradual accumulation of mutations over time. This doesn't mean that the rapid pace of human evolution isn't genuinely puzzling or that all aspects of our development are fully understood. There are still many mysteries about how and why humans evolved so quickly and acquired such distinctive capabilities, but these mysteries are best addressed through continued scientific research rather than speculation about extraterrestrial intervention. The appeal of ancient astronaut theories might reflect something deeper about human psychology and our relationship to our own evolutionary history. There's something humbling and perhaps unsettling about the idea that we're simply the result of natural processes, that our remarkable capabilities emerged through the same mechanisms that shaped every other species on the planet. The ancient astronaut hypothesis, like many origin myths, provides a narrative that makes humans special, that suggests we're somehow fundamentally different from other animals rather than simply being animals that happen to evolve in unusual directions. But perhaps the real story of human evolution is even more remarkable than any myth or speculative theory could provide. The idea that natural processes operating over millions of years could produce beings capable of contemplating their own origins, of creating art and music and literature, of developing technologies that allow them to explore other worlds and peer into the deeper structures of the universe, is in many ways more awe-inspiring than any tale of divine intervention or alien manipulation. The story becomes even more remarkable when we consider where human evolution might be heading in the future. While we can't predict exactly how our species will change over the coming millennia, we can make some educated guesses based on current trends and emerging technologies. The next 100,000 years of human evolution will likely be shaped by very different forces than those that influenced our past development, creating possibilities that our ancestors could never have imagined. One of the most significant factors shaping future human evolution will be our increasing control over our own genetic makeup. While natural selection continues to operate on human populations, its effects are increasingly overshadowed by medical advances that allow individuals with genetic conditions to survive and reproduce, by reproductive technologies that give people choices about which genes to pass on to their children, and by emerging genetic engineering techniques that will eventually allow direct modification of human DNA. The development of CRISPR and other gene editing technologies represents the beginning of an era where humans will have unprecedented control over their own evolutionary trajectory. While current applications of these technologies are focused on treating genetic diseases, future developments will likely enable enhancements that go far beyond correcting medical problems. We might eventually be able to enhance human intelligence, improve disease resistance, extend lifespan, or even add entirely new capabilities that don't exist in current human populations. This technological control over evolution represents a fundamentally different kind of change than anything that has occurred in the natural world. Instead of being shaped by environmental pressures and random mutations, future human evolution might be directed by conscious choices about what kinds of traits and capabilities we want to develop. This could lead to much more rapid changes than would be possible through natural selection alone, potentially producing new forms of humanity within centuries or decades, rather than millennia. Brain-computer interfaces represent another technology that could dramatically reshape human evolution. Current research into neural implants and brain-computer communication is still in its early stages, but future developments could enable direct connections between human brains and artificial intelligence systems, effectively expanding human cognitive capacity beyond the biological limits of our neural tissue. Such interfaces could allow humans to access vast databases of information instantly, to communicate directly with each other through technological networks, or to enhance their thinking processes with artificial intelligence assistants. If brain-computer interfaces become widespread, they could fundamentally alter what it means to be human. The boundary between individual minds and collective intelligence could become blurred, creating forms of consciousness that are neither purely human or purely artificial. The traditional limitations of human memory, processing speed, and attention could be overcome through technological augmentation, producing beings with cognitive capabilities that dwarf those of current humans. Genetic engineering and brain-computer interfaces are just two examples of technologies that could reshape human evolution. Advances in nanotechnology might allow for cellular-level modifications that enhance strength, endurance, or resistance to disease and aging. Developments in artificial organs and prosthetics could replace biological limitations with technological capabilities. Research into life extension could dramatically increase human lifespan, providing more time for learning, adaptation, and cultural development. Perhaps most speculatively, advances in space travel and planetary colonization could expose human populations to entirely new environments that would create novel selective pressures. Humans living on Mars, for example, would face different gravitational forces, radiation levels, and atmospheric conditions that could drive evolutionary adaptations over many generations. Populations living in space habitats or on other planets might diverge from Earth humans in ways that eventually produce new subspecies, or even new species entirely. The timeline for these potential changes varies enormously depending on which technologies develop and how quickly they are adopted. Some modifications, like genetic therapies for specific diseases, are already beginning to be implemented. Others, like comprehensive genetic enhancement or brain-computer interfaces, might take decades to develop and become widely available. The most speculative possibilities, like space colonization or radical life extension, might require centuries to achieve. What's certain is that future human evolution will be increasingly shaped by conscious choices rather than random environmental pressures. This represents both tremendous opportunities and significant risks. On the positive side, we might be able to eliminate genetic diseases, enhance human capabilities in remarkable ways, and adapt to environmental challenges that would otherwise threaten our survival. On the negative side, genetic modifications could create new forms of inequality, technological augmentations could undermine human autonomy, and rapid changes could disrupt social institutions and cultural traditions in unpredictable ways. The ethical implications of directing human evolution are enormous and largely unexplored. Who will decide what kinds of modifications should be pursued? How will we ensure that enhancements are available equitably, rather than creating new forms of biological class distinction? What happens to human identity and dignity if we become increasingly modified by technology? These questions don't have easy answers, but they will become increasingly urgent as the technologies that enable evolutionary modification continue to develop. There's also the question of whether technological enhancement will ultimately be beneficial for human flourishing. Many of our most valued human characteristics, like creativity, empathy, and wisdom, emerge from our limitations as much as from our capabilities. The struggle to overcome challenges, the need to cooperate with others, and the awareness of our own mortality might be essential components of what makes life meaningful and human relationships valuable. If we eliminate these constraints through technological modification, we might gain power and capability, but lose something essential about the human experience. Future human evolution might also be shaped by environmental changes that we're creating through our impact on the planet. Climate change, habitat destruction, and pollution could create new selective pressures that favor different traits than those that were advantageous in past environments. Urban living might favor individuals who can tolerate high population densities, process complex social information rapidly, and thrive in artificial environments with limited access to natural spaces. The rise of digital communication and virtual reality could also influence human evolution in unexpected ways. If significant portions of human social interaction move into virtual environments, we might see changes in how we process visual information, how we form social bonds, and how we distinguish between real and simulated experiences. Children who grow up primarily interacting through digital interfaces might develop different neural pathways and social skills than those raised in more traditional environments. The globalization of human culture might also affect our evolutionary trajectory. As populations that were historically isolated come into contact and interbreed, genetic variations that were previously confined to specific regions are becoming distributed throughout the global population. This could lead to a more genetically homogeneous human species, but it could also create new combinations of traits that produce novel capabilities or characteristics. However, the increasing pace of cultural change might actually be reducing the importance of biological evolution for human adaptation. In the past, when environmental changes occurred slowly, populations had time to evolve biological adaptations that helped them cope with new challenges. Today, environmental and social changes occur so rapidly that cultural and technological adaptations are much more important than biological ones for human survival and success. This suggests that future human evolution might be primarily cultural and technological, rather than biological. Instead of evolving larger brains to process more information, we might develop better computers and artificial intelligence systems. Instead of evolving better immune systems to fight diseases, we might develop more effective medicines and medical technologies. Instead of evolving physical capabilities to survive in harsh environments, we might create better tools and protective technologies. The relationship between biological and cultural evolution in future humans might become even more complex than it has been in our past. Technological augmentation could allow individuals to modify their capabilities temporarily, rather than permanently, switching between different enhanced states depending on their current needs. Brain-computer interfaces could allow people to access different artificial intelligence systems for different tasks, effectively giving them multiple forms of enhanced cognition that can be activated on demand. Virtual and augmented reality technologies could also blur the boundary between physical and digital existence in ways that fundamentally alter human experience. If people spend significant portions of their lives in virtual environments, the distinction between what's real and what's simulated could become less meaningful. This might lead to new forms of consciousness that are adapted to multi-reality existence, where individuals move fluidly between physical and virtual worlds. The possibility of uploading human consciousness to digital systems represents perhaps the most radical potential change in human evolution. While such technology is still highly speculative and faces enormous technical and philosophical challenges, it could theoretically allow human minds to exist independently of biological bodies, to be copied and modified like computer software, and to persist indefinitely without the limitations of biological aging and death. If consciousness uploading becomes possible, it could lead to forms of existence that are barely recognizable as human in any traditional sense. Digital minds could be duplicated, merged, modified, and enhanced in ways that biological minds never could. They could exist in virtual environments that have no physical constraints, experience time at different rates, and access information and capabilities that are impossible for biological brains. Such developments would raise profound questions about personal identity, continuity of consciousness, and what it means to be human. Would an uploaded mind still be the same person as the biological brain it was copied from? Would digital beings that could be copied and modified still have individual identities? Would forms of consciousness that could be enhanced and modified at will still experience life in ways that are meaningful from a human perspective? These questions might seem like science fiction, but they're becoming increasingly relevant as neuroscience advances our understanding of how consciousness works, and as computer technology approaches the complexity needed to simulate brain function. Even if consciousness uploading never becomes possible, other forms of human-machine integration could raise similar questions about identity, autonomy, and what defines human nature. The timeline for these various possibilities spans from the immediate future to the distant speculative horizon. Genetic therapies for specific diseases are already being developed and implemented. Enhancement technologies that go beyond treating diseases might become available within decades. More radical possibilities like consciousness uploading or space colonization might require centuries to achieve, if they're possible at all. What seems certain is that the next phase of human evolution will be unlike anything that has occurred in the natural world before. For the first time in the history of life on Earth, a species will have conscious control over its own evolutionary trajectory, the ability to direct changes rather than simply responding to environmental pressures. This represents both an unprecedented opportunity and an enormous responsibility. The choices we make about human enhancement and modification over the next few centuries could determine the future of our species for millennia to come. Unlike biological evolution, which operates through gradual changes that can be reversed, if they prove maladaptive, technological modifications might create permanent alterations that can't be undone. We might have only one chance to get these decisions right, making it crucial that we think carefully about what kinds of beings we want to become. This brings us back to the central mystery that has guided our entire exploration of human evolutionary strangeness. Why did our species develop so rapidly and acquire such unique capabilities in such a relatively short period of time? What made human evolution so different from the gradual, conservative changes that characterize most other species? Perhaps the answer lies not in any single factor, but in the unique combination of circumstances that shaped our development. The expansion of African forests due to climate change provided new environmental opportunities. The development of bipedalism freed our hands for tool use while creating new challenges for survival. The growth of social group size created pressure for better communication and cooperation. The mastery of fire provided energy resources for brain growth while creating new opportunities for cultural development. Each of these factors by itself might not have been sufficient to drive the remarkable changes that characterize human evolution. But together, they created a perfect storm of selective pressures and opportunities that pushed our ancestors in directions that no other species has ever explored. The feedback loops between biological and cultural evolution accelerated the pace of change, creating the runaway development that distinguishes human evolution from all other evolutionary processes. The result was a species that became capable of understanding its own origins, of deliberately modifying its environment and eventually itself, and of contemplating possibilities that extend far beyond the biological constraints that limit other forms of life. We became, in effect, evolution becoming conscious of itself, the first species capable of directing its own future development. This self-awareness brings both tremendous power and tremendous responsibility. Unlike our ancestors, who were shaped by forces beyond their control, we have the ability to choose what kinds of beings we become. The decisions we make about genetic modification, Technological enhancement, environmental management, and space exploration will determine not just our own futures, but the future of consciousness itself in the universe. In many ways, we're still the same species that learned to control fire, developed language around ancient hearths, and created the first stories about where we came from and where we might be going. We're still driven by the same curiosity, creativity, and desire for connection that characterized our earliest ancestors, but we're also something new in the history of life, a species that has transcended many of the limitations that constrained all previous evolution. The strangeness of human evolution, the rapid pace of change and the acquisition of seemingly impossible capabilities might ultimately be explained by the emergence of this new form of evolutionary process. Once cultural evolution began to interact with biological evolution, once learning and teaching began to supplement genetic inheritance, the normal rules of evolutionary change no longer applied. We entered a realm where change could be directed rather than random, where improvements could be shared across populations rather than emerging slowly through mutation, and where the pace of development could accelerate far beyond anything possible through biological processes alone. This cultural evolutionary process is still accelerating. The rate of technological change continues to increase. The pace of scientific discovery shows no signs of slowing, and our ability to modify ourselves and our environment grows more sophisticated each year. If the last few million years of human evolution seem rapid and strange, the next few thousand years might be even more remarkable. Perhaps the most profound realization from our journey through human evolutionary strangeness is that we're not just products of evolution, we're participants in it. Every choice we make about how to live, what technologies to develop, and what values to embrace contributes to the ongoing process of human development. We're not just studying evolution from the outside, we're creating it from the inside. This perspective transforms how we think about ourselves and our place in the universe. We're not just observers of cosmic processes, we're active participants in them. The consciousness that allows us to contemplate our origins might itself be one of the most significant developments in the history of the universe, the moment when matter organized itself in such a way that it could reflect on its own existence and actively direct its future organization. The story of human evolution is far from over. In many ways, we're still in the early chapters of what promises to be an extraordinarily long and complex narrative. The biological and cultural innovations that distinguish us from other species might be just the beginning of what's possible when evolution becomes conscious and deliberate, rather than blind and random. As we continue to unravel the mysteries of our past and contemplate the possibilities of our future, we're engaged in perhaps the most important project in the history of life on Earth, understanding and directing the development of consciousness itself. The strangeness of human evolution might not be an anomaly to be explained, but a preview of what becomes possible when the universe begins to wake up and take control of its own development. Whether through genetic modification, technological enhancement, space exploration, or forms of development we can't yet imagine, the future of human evolution promises to be even stranger and more remarkable than our already extraordinary past. We're not just studying the mystery of how consciousness emerged from matter, we're actively participating in the next phase of that emergence. And in the quiet moments of reflection, perhaps lying in the darkness as sleep approaches, we can feel the weight and wonder of this responsibility. We're the first species that evolution has produced that can consciously direct its own future development. We're the universe's first attempt at understanding itself from the inside. We're matter that has become capable of contemplating its own existence and actively shaping its future organization. The choices we make in the coming years and decades will echo through millions of years of future development, determining not just what kinds of beings our descendants become, but what consciousness itself becomes as it continues to evolve and develop throughout the cosmos. In every decision about genetic modification, artificial intelligence, space exploration, and technological development, we're writing the next chapters of the most important story ever told, the story of how the universe wakes up. The fire that our ancestors learned to control hundreds of thousands of years ago was just the beginning. The symbolic language they developed to share ideas and build cultures was another step in the same process. The myths and stories they created to understand their origins and contemplate their destinies were early attempts at the same project we're engaged in today, understanding what it means to be conscious beings in a vast and mysterious universe. As we drift towards a sleep, minds filled with these contemplations of deep time and vast possibility, we can appreciate that we're part of something much larger than individual human lives, or even human civilization. We're participants in the ongoing evolution of consciousness itself, contributors to a process that began with the first stirrings of life on Earth billions of years ago, and that might continue for billions of years into the future. The strangeness of human evolution isn't just an interesting scientific puzzle, it's a glimpse into the extraordinary creativity and potential of the evolutionary process when it becomes conscious and deliberate. We're not just the product of evolution, we're evolution's newest experiment in self-awareness and self-direction. And like all the best experiments, the results are impossible to predict but certain to be remarkable. In the gentle transition towards sleep, as conscious awareness softens and the rational mind gives way to the imagery and symbolism of dreams, we become participants in another aspect of the remarkable process that distinguishes human consciousness. Our sleeping brains will spend the night processing and integrating the experiences of the day, weaving them into the vast neural networks that give rise to memory, understanding, and imagination. This nightly process of dream consciousness might itself be one of the key innovations that drove human cognitive evolution. While other animals sleep and probably dream, human dream consciousness seems to be uniquely rich and complex, capable of generating the kind of symbolic thinking and creative problem-solving that characterizes our species. The same neural processes that create our elaborate dream worlds might be essential for the symbolic language, mythological thinking, and creative imagination that define human culture. As sleep approaches and the conscious mind prepares to hand control over to the dreaming brain, we can appreciate that even this basic biological process has been transformed by human evolution into something unique and remarkable. Our dreams don't just process the events of the day, they generate new ideas, explore possibilities, and create the kind of associative thinking that drives innovation and creativity. The firelit gatherings of our ancestors, where the first human stories were told and the first songs were sung, might have been the beginning of the same process that continues in our sleeping minds each night. The symbolic thinking that allows us to find meaning in metaphor, to see connections between disparate experiences, and to imagine possibilities that don't yet exist, operates in dreams just as it does in waking consciousness, perhaps even more freely and creatively. In this sense, every night's sleep is a return to the creative consciousness that might have driven human evolution, a temporary retreat from the practical concerns of daily life into the realm of pure imagination and possibility. The dreams that visit us in the quiet hours before dawn might be echoes of the same cognitive processes that allowed our ancestors to develop language, create art, build cultures, and contemplate the mysteries of existence. As we surrender to sleep, mind still resonating with contemplations of evolutionary time and cosmic possibility, we join the countless generations of humans who have drifted into dreams beneath starlit skies, around dying fires, in caves and huts and cities, all participants in the same ongoing experiment in consciousness that began with the first stirrings of symbolic thought hundreds of thousands of years ago. The story of human evolution continues in our dreams, in our daily choices, in our scientific discoveries and artistic creations, in every moment when consciousness turns its attention to understanding itself and shaping its future development. We're not just studying the mystery of how mind emerged from matter, we're actively participating in the next phase of that emergence, writing new chapters in the strangest and most wonderful story ever told. Even as individual consciousness fades into sleep, the larger consciousness of our species continues its remarkable journey through time and possibility, carrying forward the flame of awareness that was first kindled around ancient fires, pursuing questions that our ancestors could barely imagine and creating possibilities that we ourselves can only dimly perceive. In the vast context of cosmic time and space, human evolution remains an ongoing experiment in what becomes possible when the universe develops the capacity to understand and direct its own development. The gentle drift towards sleep becomes a metaphor for the larger rhythms of consciousness and evolution, the cycles of awareness and rest, of exploration and integration, of questioning and understanding that drive the ongoing development of mind in the universe. As individual awareness dissolves into the timeless realm of dreams, It rejoins the vast ocean of consciousness from which it emerged, carrying with it the day's experiences and insights to be woven into the ever-growing tapestry of human understanding and possibility. And in the morning, consciousness will emerge again, refreshed and renewed, ready to continue the remarkable journey that began millions of years ago when the first humans learned to control fire, developed language, and began to contemplate the mystery of their own existence. The story of human evolution is far from complete, and each new day brings opportunities to write new chapters in the strangest and most wonderful narrative in the history of the universe, the story of how matter learned to think, to dream, and to consciously direct its own future development. The fire still burns, passed down through countless generations from those first hearths where our ancestors gathered to share stories and contemplate the stars. The language still flows, carrying thoughts and dreams and possibilities from mind to mind across the vast networks of human consciousness. The questions still call to us, inviting exploration of the deepest mysteries of existence and the greatest possibilities for future development. We remain participants in the same evolutionary process that shaped our ancestors, but now we're conscious participants, capable of understanding and directing the changes that will determine what our species becomes. In every choice about technology and values, in every scientific discovery and artistic creation, in every moment of wonder and contemplation, we're contributing to the ongoing evolution of consciousness itself. The strangeness of human evolution continues, becoming stranger and more wonderful with each passing day as we push the boundaries of what's possible for conscious beings in an infinite universe. We're not just the products of an extraordinary evolutionary process, we're its active agents, the means by which the universe continues to wake up and discover what it might become. As sleep claims consciousness and the rational mind gives way to the symbolic realm of dreams, the larger story continues, carried forward by the collective intelligence of our species and all the conscious beings we might encounter or become in the vast reaches of space and time. The journey that began with the first stirrings of life on Earth continues through us and beyond us, an epic of consciousness exploring its own infinite potential. In the gentle transition from waking awareness to sleeping dreams, we participate once again in the rhythm that has sustained human consciousness for hundreds of thousands of years, the daily cycle of exploration and rest that allows the mind to process new experiences and prepare for new discoveries. Tonight's dreams will weave together the ideas and images from our contemplation of human evolutionary strangeness, creating new connections and possibilities that might inspire tomorrow's insights and innovations. The ancient fire still burns in the neural networks of our sleeping brains, the symbolic language still flows in the metaphors and narratives of our dreams, and the questions that drove our ancestors to contemplate their origins and destinies still call to us across the bridge of sleep, inviting continued exploration of the deepest mysteries and greatest possibilities of conscious existence in an evolving universe. We sleep not as passive observers of evolutionary processes, but as active participants in the ongoing development of consciousness itself, carrying forward the flame of awareness that our ancestors kindled around fires beneath ancient skies, pursuing the same fundamental questions about who we are, where we came from, and what we might become in the vast expanse of cosmic time and possibility. The evolutionary journey continues even in sleep, even in dreams, even in the quiet moments when individual consciousness dissolves back into the larger ocean of mind from which it emerged, ready to surface again with new insights and renewed wonder at the strange and beautiful story of how the universe learned to contemplate itself and began to direct its own future evolution toward possibilities we can barely imagine but actively help to create with every breath, every choice, every moment of conscious awareness in the great adventure of existence. The mysteries deepen, the possibilities expand, and the story continues, stranger and more wonderful than any myth or legend could capture, as real as the neural firing patterns that create consciousness, and as vast as the cosmic processes that gave birth to matter, capable of contemplating its own existence and shaping its future development across the infinite reaches of space and time. We are the universe waking up, and the dream has only just begun.